So if you could slowly find your seats. Our first presentation this morning is Satoshi Miyazaki-san from NAOJ going to talk about Hyper Supreme Cam and the first data release.
Good morning. My name is Satoshi Miyazaki, working here at the NAOJ for mainly instrumentations, and I'm also interested in the observational cosmology. And today I'm going to talk about our camera, as well as the first public data release occurred just a few days ago. Before I start, let me briefly summarize what happened before on the visible camera surveys. The first one that I mentioned here is a Surround Digital Sky Survey. As probably all of you knows about this famous survey. This survey is based on the 2.5 meter telescope, which is dedicated for the survey, which is located at Apache Point in New Mexico. And it covers 10,000 square degrees down to R of 23rd magnitude. So this is very, survey. This data is, of course, released publicly, and the revision of the data released, repeated. And this is now, I think, DR13 is the most recent one, and the data is, retrieved by any homes. Like, for example, this is a sky server that they provide us, and you can see, wherever you want by clicking the mouse and, and zoom in and zoom out. The second one that I introduced here is Canada, Hawaii, France Telescope Legacy Survey. This is 3.6 meter CFHT. I'm sorry, this is not the dedicated telescope, but this is typo. And they covered 170 square degrees down to 24.7. So this is very, deeper than what SDSS achieved because of thanks to the larger aperture of this telescope. They also released the data as is shown here, and because it's deeper, the number density of the galaxy is much more, large, as you can see here. So when we make the survey design, there's two key parameters. One is, one is width, and the other one is depth. And when you go to the right, it's wider, and when you go upward, it means fainter. And Surround Digital Sky Survey is located right here, nearly, almost 10,000 square degrees. The whole sky is 40,000 square degrees, and so nearly all sky. The quarter of the sky is covered by already Surround Digital Sky Survey. And CFHT is not that wide, but deep, like nearly 25 in R1. And our survey is located right here, which is 10 times wider than CFHT legacy survey and 1 magnitude deeper than the CFHT legacy survey. So when you go fainter by 1 magnitude, the number of galaxies are nearly 4 times or 5 times, and we also have a 10 times wider widths. So the number of galaxies, catalog number of galaxies would be like 40 times or 50 times larger than what CFHT legacy survey has achieved. And this is the parameter of what we call wide survey, wide HSC survey. And we also have a deep design as well as ultra deep. And those two are located somewhere around here. So we have a three-layered survey, wide, deep, and ultra deep. And deep is like 25 square degrees, and ultra deep is only 4 square degrees, but much deeper compared with those wider surveys. So all the data is public now. So this is how our camera looks like. So in short, this is nearly a 1 gigapixel digital camera, and its weight is 3 tons and 3 meter high. Because it's a camera, there's a lens and filters, shutters, and CCDs. So, of course, the primary mirror is located 15 meters away from this camera, and 8.2 meter, primary mirror is, of course, the part of the optics. And combined with, and the first lens diameter is 80 centimeter, 82 or 83 centimeter in aperture. And the focal plane physical dimension is nearly 50 centimeter across. And this is the prime focus camera, which means that the camera is inserted from the top and facing down, and this primary reflects the light back to our camera, and through this lens, you have a sharp image of 1.5 square degrees, and physical dimension, as I said, 50 centimeter. The detector features a very high red QE in red band, thanks to the thickness of the CCDs. This CCD, thickness of the CCD is 100 times thicker than the conventional, commercial sensors. And QE that we have here is very, very high in QE, which means that, hunting the high Z objects it's good at hunting these high Z quasars and high Z galaxies, thanks to this thickness. This is a comparison in QE compared with this CFHT camera. We have a very, very high QE in red. The CCD itself is small, like 3 times 6 centimeter. And our focal plane is much larger, so we have to pave the focal plane with 116 CCDs like this. And here's, you can see the installation process made at this, in the clean room at the observatory. So one of the CCD is, as I said, 3 centimeter times 6 centimeter, and it is, placed one by one, and the focal plane is formed just like this. So when we finish, the cameras, looks like this. And here's 116 CCDs, but not all of the CCDs are used for the science. Among them, 4 CCDs are dedicated for the autoguiders, and 8 CCDs are used for the focusing. Those 8 CCD has, offset and it always takes a focus image to monitor the shift of the focus position. And all the electronics is inside the back of this cold plate. CCD is cooled down to minus 100 degrees in order to suppress the dark current, and all the the electronics are behind this focal plane and connected internally. So this is basically the digital camera. We feed the digital input and we have a digital output. And there's no analog signal chain across this dual, vacuum dual, in order to reduce the number of wirings. So here's a final assembly phase of a vacuum dual. Here's a 116 CCDs, and it's a vacuum dual jacket. And here's an entrance window whose glass thickness is 37 centimeter. So the weight is like a 20 kilograms. So it's very heavy. The dual is assembled together to some electronics and controllers, and looks like this. And here is a shutter, and the light comes from the bottom, entering into the camera. The CCD is facing down here. So because the focal plane is large, the filter itself is also large. It's like a 60 centimeter, and all interference membrane filters. Shutter, this is a customarily designed and made for this HSC camera, and it's looks like an ordinary camera focal plane shutter, and we can run this screen at the same time to make the shorter exposure time. And but typical exposure time is like a 2 minutes or 3 minutes or 4 minutes, so we don't have to run this screen so much. So this 1 second movement across is fast enough. So here's how the first lens looks like, and the assembly of the first, the lens is something like this. So here's a cross-sectional view of the camera, the lens, and the duals. And here we have filter exchangers. There's a 3 filter storage on each side, and when we install the filter, this part is flipped down horizontally, and we extract the filters and then insert another filters from the side. And then after the installation, this filter exchanger mechanism is flipped up in order to reduce the vignetting of the light, because the camera is inside the beam of the telescope. So here is how we do the image processing. Because we have 116 CCDs with 4 channel, we have more than 400 images which have to deal with. And so the raw data looks like this, and then we correct the sensitivities and also the distortion of the optics. So we have to warp the original image slightly to map onto the correct sky coordinate. And then we stack them together. We usually, these are the pointing to fill those CCD gaps, and then these are the images are stuck together to obtain the final image. So let me show you how the image of a camera looks like. But before I start, let me start from this M31 image, which was taken in the early 1991. This is one of the first flight Subaru image, and we put the 6 CCD camera at the Cassegrain focus of the Subaru, and I think this is only like a couple of arc minutes across, And we took the part of the arm of the M31, and we obtained this, stars, basically, of the M31 galaxies. And then this was released, but nobody understands what this is because of this narrow field. And we need to explain exactly that this image means that this, the part of the M31. And so here's what we had in early 1999. And then we have a prime focus ready, and we have much wider area. And then more than 10 years later, we have now mostly cover the whole M31 using the Hypers prime cam. So we had engineering first right in January 2013, and this diagram shows that how our image, the image quality is good over the field of view. So this contour shows that, all across the 1.5 degree field, we have very nice thing like 0.4 to 0.45 over the area, which is fairly unique on the considering the large aperture, like 8.2 meter. Here's the same statistic. Let me speak this. So Hypers prime cam is very unique because we combine the large aperture of 8.2 meter and 1.5 degree diameter and the sharp image, thanks to the the superb image natural seeing at Mauna Kea. Okay. So so this is quite essential for us because the dark matter mapping by the weak gravitational lensing is our major science case, and this is features is quite necessary for main science. So let me skip a couple of slides to show you how the lensing looks like, but let me go through this. Maybe you can see. So now, observing, the survey started after March 2014, and it would take 5 or 6 years to complete our design survey design. And first public data release is made a couple of days ago, and that is 1/10 of the final data product. But it already contains 7 million objects, mostly galaxies, and the coverage of the area is 108 square degrees in wide, 26 in deep, and 4 in ultra deep. And you can see find out the link directly from the top page of the Subaru how to access this data. But let me show you how it looks. Basically, this release is for the scientists, and they will typical usage of this data is through the SQL query. So when you are interested in some particular type of the objects, you generate the SQL form, and then that will be pasted onto this window, and then after the data is ready, you can retrieve the results of the objects, something like this. And of course, you can fetch by many forms. And this is a typical catalog usage, which is also true for the SDSS. So now astronomers have to know the syntax of the SQL. And however, for the public, maybe the image viewer is more important. So let me show you how it looks like. So this image viewer we call HSC map. Okay. So let me start from this SDSS one. So this is SDS Sky Viewer, and here's a, I don't know why this chose this galaxy as a top page, but when you open this Sky Server, what you will see is these galaxies at somewhere at the near equator. And this is, so this is what we have now. This is the same galaxies. But because it's deeper, we have, and sharper, you have more detail. And you can zoom in to the, this pixel is actual pixel, 0.2 arcsecond across. So we release everything down to the every pixel. Each pixel you can see our data. And so let me move out from this here. So here is one of our survey field called Y12H. So this is nearly the equator at the right ascension of 12. And this green area shows that where we observe. So this is part of the wide survey. And here is another wide survey area, which we call Cosmos. And here is gamma 009 field. And you can zoom in wherever you want. And, something like this. And when you move out more and more, this shows how our survey area is located. So mostly on the equators, and some northern field is also observed. This is a collaboration work with Margaret Gerrards at CFA. She has a tremendous effort put onto this field to have spectroscopic samples. So we really want to, correlate with our data with what she had. And oh, by the way, we have when we while we are doing some commissioning run, we have some of the, let me show you. Which one? Wait a minute. Here's M31. So this is what I showed you on the screen, but you can zoom in wherever you want. So I hope that this is useful for some of the outreach program, because you can zoom in wherever you want like this. And here's a beautiful star-forming region. Accent is those are H-alpha emissions, so you can see the whole bunch of H-alpha region near the edge of this dark clouds, and this is very impressive. And also we have Orion. Here is, this is not a part of a survey, but this is taken through during the commissioning run. And some of the guys spend a lot of time to assemble all this image together to, looks like nice. And here you can see a whole bunch of, texture of those nebula. So those are all public, and you can look at access through our website. And so, for example, there's lots of cluster of galaxies also, located through lensing. So this is a gorgeous, dense fields. So hope that, I'm not sure how, we can use this sort of image for the outreach. And we start talking with some of the experts here in Japan, how to, use this image for the education and public outreach. The discussion has just begun. Let's see what else I have. Because we have a multiple exposure, the moving objects look something like this. While we are taking the multiple exposure, the moving object is moved across the field. And because we have a monochromatic image, this particular image was taken through the red band. And because of that, it's purely red, looks purely red. So, okay. So I think this is it. We have a whole bunch of, object here because it's 70 millions. And, looking through this HS view is very, very interesting. And I hope that people enjoy it. And your, presentation. So let's see what else I have. Okay, I think this is it for now. Thank you very much.
Thank you so much. Are there any questions? Comments? Mark?
Thank you. Those images are incredible. And the viewer is really nice as well. Do you provide access to the three-color images in some sort of image query service like SkyServer?
Your question is, you want to have more, raw data or?
Yeah, well, something like a tile server. If I wanted to make a request for a cutout or something.
Oh yes.
Of the color image.
Well, basically all the data is available, but I have to check whether the easy interface is ready, because you can retrieve some chunk of the data, but it is already formatted. So it might be larger for the general public, but we have to check. But there is the way to retrieve all the data.
Okay. Thank you.
Anyone else? Akata-san?
Good morning. Thank you, Miyazaki-san. Very impressive data and Subaru HSC project. So I have a question for last 2 months and first data opened for public all over the world. So if anyone, amateur astronomer or student, to find a new object or some scientific data, so they should they know inform your group before publish or open to?
No. There's no limitation, because this is purely public. You can do whatever you want. Of course.
totally free to use and publish or some writing paper and others free?
Of course.
Okay, thank you so much.
Because this is part of,
Planetarium, these CG creator use no free to use, not to
Yes, this is not the entire data set. The part of the data set is ready for public, and some other data sets are still, private.
Please use creators and planetarium parts.
Yes, there's no sort of, limitation. You can freely use, of course, to any, purpose.
Thank you. This was very impressive, so thank you so much. Let's give the speaker a hand. Next up, Masaaki-san, your co-author, Yuji Shirasaki, also here. So, but Masaaki-san will start, also from NAOJ, and we'll talk about the Japanese Virtual Observatory ALMA FITS Data Archive.
My name is Masaaki Hiramatsu, the East Asian ALMA Public Outreach Officer of NAOJ. I will introduce about the Japanese Virtual Observatory's ALMA FITS Data Archive. As a first talk of this presentation, I will introduce about the ALMA and its data structure. So I believe that many of you know ALMA observes the radio waves to explore the cool universe, for example, for the formation of stars and planets and galaxies, and searching for the organic molecules in the universe. And with 66 antennas in Chile, ALMA achieves unprecedented sensitivity and resolution. So the ALMA is now changing the world of astronomy. And this is a huge international partnership of East Asia and the ESO member states and North America and the location country, Chile. And ALMA started the science operation 2011, and so far more than 550 scientific papers have been published based on the ALMA data. And some of them based on the data archive. So the many astronomers send a proposal to ALMA and obtain their own data, but after the proprietary period, the data were open on the ALMA archive, so you can freely download the data and to write a paper. And ALMA consists of 3 components. The one is the 12-meter array. It consists of 50 12-meter antennas and distributed up to 16 kilometers. And there is a smaller part. This is a major contribution from Japan to the ALMA project. Here is a 7-meter array, 12 7-meter diameter antennas, and there are 4 12-meter antennas. This is a total power array. By adding this 7-meter array and total power array, effectively ALMA obtains wider field of view, but still much smaller than the Harper Spectrum, of course. And how ALMA changing the world of astronomy. So here this is iconic HL Tau image, the young star, and with the planetary disk. And 5 years ago, one interferometer in California observed the same source. So this is how ALMA moved forward. And ALMA is a radio telescope. So the ALMA observed wide range of radio frequencies from 30 to 950 gigahertz. So ALMA divides this frequency into 10 bands. So for each band, we have a dedicated radio receiver in a cryostat. So we can observe from the frequency of 31 to 950, and here is the corresponding wavelengths from roughly 1 centimeter to 0.3 millimeter. Still, band 1 and band 2 is in development phase, and band 5 is a production phase. But other band 3, 4, 6, 7, 8, 9, 10 is open for the science observation and producing many scientific results. And these frequency bands correspond to the atmospheric window in the Changnan, where the ALMA locates. And especially for the higher, here is the frequency versus atmospheric transmission diagram. And the curve is a transmission. And here is a 100% transparent. So there are two curves. One is a Changnan in Chile, and the lower one is Mauna Kea. Especially in the higher frequency, the sky in northern Chile is much more transparent compared to the Mauna Kea. So especially in band 9, band 10 is very unique for observation in this location. So, and other frequency range is basically the absorption by oxygen or water vapor. So, and ALMA produces 2D or 3D datasets. So usually we astronomers use this 2D data to analyze the continuum. This is basically the light from the dust particles. And also, of course, we have molecular lines, the light from molecules, and this data set have 3 dimensions. The third dimension is the frequency or velocity. So we can construct the 3D data cube from the data set. So this is a visualization of the famous spiral star, the R Scarptoris. And here is this dimension is a velocity, not a real 3D structure in the universe. So if we use this one into the public, then we have to explain this is velocity axis. So maybe sometimes it's difficult to explain. And compared to the hyperspectral IMCAM, ALMA has a very small field of view. So that the size of this iconic HL tau image is 1.5 arc seconds. And typically, the ALMA field of view is 20 arc seconds. So with mosaicing this small field of view, the total map size can be as large as a few or several arc minutes. So for example, this is a Subaru image of the M42, the Orion Nebula. And this white box, the size of this white box is 3 arc minutes. So ALMA somehow can map this range, but it's far from the field of view of the hyperspectral IMCAM. So ALMA is dedicated to image small object with very high resolution. And here I explained the ALMA data flow. So the Joint ALMA Observatory in Chile make observation and produce raw data, and raw data are sent to the ALMA data archive. And the support astronomers in ALMA regional support centers download the data from this archive, then make data reduction and quality assurance, then upload raw data and FITS file. And this raw data and FITS file will be distributed to the original astronomer who proposed the observations. So the proprietary period is 1 year. So after 1 year, this data is open in this data archive, and anyone can download or access this data. So this contains a FITS file, so the archive scientists can use the FITS file, and they do not have to analyze or make an image from the raw data. So this is a very important point in the ALMA data archive. So the main archive is located in Santiago, Chile, and this archive is just copied to the 3 data archive in Europe, Japan, and the US. And because ALMA has so many components and so many frequency bands, the data structure is somehow complicated. So here is the one example of the one data set. So astronomer submit one proposal, right? One proposal. And in this proposal, the astronomer wants to observe at one target with band 3 receiver and band 6 receiver. So in this case, astronomer have to make a science goal for each frequency band. And one science goal has 3 observing unit set for 12-meter array, 1 for 12-meter array, 1 for 7-meter array, and 1 for total power array. And within this observing unit set, there are several execution blocks. And Joint Atom Observatory execute blocks. And this block takes 40 minutes to 1 hour for observation. And Joint Atom Observatory repeat to execute this execution block until the noise level reach the original request from the proposer. So in the ALMA data archive, there are so many execution block data are listed. So it's not so easy to look inside the ALMA data in the original ALMA data archive. So you can download the ALMA data from the ALMA data archive. And you can go to this ALMA data archive through the ALMA Science portal. So you can choose either your nearest site in Japan and US and Europe. So here is the ALMA Science portal in Japanese, and here is data. So you can go to the data archive. Okay, then here is the archive query. Then here is the top page of the ALMA data science archive. It's very primitive compared to the sophisticated HSC data archive that you can use here with, for example, famous HL tau image and submit. Then you have a small window from the Aladdin, and in the bottom side, here is a list of the data. This red one is not open yet to the public. So these data are open in, for example, this is April 1st, July 2nd, so you can wait until, you should wait until this date. And check and submit to download request. Then you will have a list of the data set. Takes time. So it takes time. So the result should be something like this. So the list of the data set, and each of them have several gigabytes or tens of gigabytes. So it's very time consuming to download it. And most difficult part in this official ALMA data archive is probably you cannot estimate or you cannot estimate whether this data is useful for you. After downloading this huge data set, and then the person understand, oh, this is not useful for me. This is not good style. So to overcome this difficulty, the Japanese Virtual Observatory developed by the Astronomy Data Center in this NAOJ provide a quick look system and a very sophisticated infrastructure for data downloading. So the latter half, the Shirasaki-san from the Astronomy Data Center of NAOJ will introduce the JVO ALMA data archive.
Then I talk about our JVO ALMA FITS archive, and at the end of the talk, I'll show you a demo how to use this data archive system. As introduced by Hiramata-san, the official ALMA data archive is located at this ALMA science portal. But there are another ALMA data archive here, that is JVO ALMA FITS archive. It is available here, and it is linked from JVO project site. This is developed with a collaboration between Astronomy Data Center and ALMA software team of NAOJ. The future of this JVO ALMA FITS archive is it's very simple data search interface that it provides. All the data are linked from the top page, so you can get to the data just by clicking several times. So you don't need to type a keyword, any keyword, so you can easily browse the data, all the ALMA data from this system. And of course, you can also search the data by specifying object name or by coordinate. And we are also providing the graphical sky map type interface. We are calling it JVO Sky. I'll introduce that later. And another important feature is we provide a quick look functionality of the content of the data before downloading the data. This has become very important if ALMA data become very big. So we you can check that, you can see the thumbnail of the image and the spectrum when selecting the data. And if you want to look at the data more in detail, you can use the ALMA WebQL. That is a web-based visualization tool for looking the ALMA 3D cube. It should be noted that there are caveats in using the JVO ALMA FITS archive. One is the FITS data that is provided at the JVO ALMA FITS archive, and also the ALMA archive doesn't contain all the, for some of the FITS, that it may doesn't contain all the frequency range or spatial region. So if you want more complete data set, you must derive the raw data by yourself. But in future, all the complete data may be delivered as a FIT file. And there is a limitation in the number of search parameters. Currently, we are implementing the search by object name, spatial coordinate, project ID and title, and observed frequency range. But in future, we will add more advanced functionality, like current ALMA archive. And this is the top page of the JVO ALMA FITS archive. And there are several tabs, and if you select the target name tab, you can the data are sorted by alphabetic order, And this here, target name is the name of the source as registered by PI. So it is not necessarily the name of the target, but it can be a name of the field, but that is arbitrarily assigned by project in PI. If you want to search the data by a proper name of the object, please use Symbol tab or Coordinate tab. Also, it is also possible to search by keyword, but you can specify keyword by filtering the data. Clicking the target name link, the list of data that corresponds to this target name is appear, and here you can see the thumbnail of the image and spectrum. By looking at this thumbnail, you can select the data you want to download, and then finally you get to the download page. And clicking the download button, you can get the data of ALMA. This is a search by. You can search the data by coordinates, especially the center coordinate and the radius of the search region. And we also offer this sky map type GUI. You can find this map can be rotated. You can rotate this map like a Google map. Then if you move up in the up until the coverage of the data appear, the link to the data download page appear in the information window. And you can also search by project code and title, and also frequency at this project code or code tab. And this is a download page. As already mentioned, the download, you can download by clicking download button. And you can also invoke the WebQL, that is a web application, which enables a user to view the content of data, and also you can cut out the part of the data cube. And if you want more detailed visualization tool, you can use a Visage, that is a desktop type application. Using this application, you can look at the PV diagram or channel map of the ALMA cube. Here is I introduce ALMA WebQL and go to the demo. And the main feature of ALMA WebQL is that, as shown here, you can look at both the image and spectrum at once very easily. And the image of select region is zoomed at the corner of the screen. And also this spectrum calculated by integrating for this select region, that's updated in real time. So you can easily check the position dependence of the spectrum. There are many other features I'll introduce by so you need to go to first JVO project page. Please find it on the Google search. And here, this needs to English. There are links to the JVO portal. And click here. You can get the top page of JVO portal. And there you can find the ALMA section here. And the ALMA SV fit data is for taking data of science verification data, or ALMA, that is observed by observatory. ALMA fits archive contains the data observed in the open use program. And we also provide some demo. Okay, I only show you a demo. For example, there are protoplanetary disk data here. So let's look at this data. And by changing the size of the selected region, both image and spectrum real time change. And so moving this way, you can check the position dependence of the spectrum. And also by selecting larger width and clicking the shift and move the cursor to the bottom and you can select the spectral range. Then you can look at the image for the selected spectrum band. To go back, please press Ctrl R. Okay, and you can also change the color map from 7 kind of type of map this way, and there are many options to download the full data. Please click here, and to download the partial data, select like this. Then you can download only the selected part of the data. And here there is a user guide, so you can read this user help page to how to use this system. Thank you. That's all.
Thank you so much. Excellent. I now know a lot more about ALMA than I did before, and I did know quite a bit. Thank you. Questions, Doug?
Yeah, this is really a beautiful interface, and I have to say, being a North American and going through the North American portal, you have a lot better tools than we do. So one question, if I as an astronomer take data set and do something to it, make moment maps or some sort of derived properties, does your archive allow for a user to contribute back some processed or derived data or imagery if it's files?
Currently, no. I think there are only the feedback to the ALMA data archive is allowed to the support astronomers in the ALMA regional support centers.
I had a question about observations of noting how small a field of view you have. This is really a question about research, and I did a quick search and I wasn't finding much, but looking for the earliest galaxies and looking at early galaxy structure, just if you care to comment or know anything about that. Thank you.
So basically the finding interesting object will be done by other telescope. For example, the Hubble HST or the other single-dish radio telescope. Then astronomers find interesting object. Then they use ALMA to look deeper.
Yes, that's the process. I was asking, do you know of any research that's doing that and looking at early galaxy structure? That was the question.
I'm sorry, I can't understand you. You are in the point.
I want to know if any astronomers are looking at very early galaxy structure with ALMA. Thank you.
Okay, so yes. For example, ALMA provides the image from the galaxy at z equals 7.5. So the redshift 7.5 corresponds to the one 13 billion years ago. So there are several data for the early galaxies, but it is still very blur, very diffuse image, and it's difficult to look the detailed structure of the early galaxies still.
It's just that ALMA has the highest resolution possible.
Yes.
And that's what's so exciting about it. Thank you.
But there is also very high redshift stuff going on. There's some redshift 8, 9 stuff coming out in about a week or so. So good stuff.
Yeah, I saw the Cosmic Dawn piece in Nature, where you have galaxies out to about over 11. So pretty amazing. Yeah, it's from the HDF. So thanks.
Yeah, but also ALMA is really getting out there due to the emission line, so it can look at CO and things, dust.
Thank you.
Very interesting early forming dust, puzzlingly early. So wait about a week or so for that. Is there a final question while we're getting set up here? You need a hand, Seiko?
Oh, well, I'm just waiting for the...
Okay, good. A final question about ALMA or browsing or looking at the data? All right. Well, let's thank the speakers again. Our next speaker is Saiko Hayashi-san from the Subaru telescope, NAOJ. And
yep.
Saiko will talk about connecting the real sky and your sky in the classroom or even in your home.
Yep. Okay. Well, good morning, and my mind is already in the afternoon mode. So is my laptop. So it's kind of slow. While waiting for this system to set up, what I want to talk about today is not the data from the Subaru telescope, but something small that is sitting on the rooftop of the annex building. But that is very important. When you talk about dark matters, distant objects, exoplanets, sometimes people lose sight of what's up there, actually. So in order for those layperson to connect back to the real sky, we have some tools. That's what I want to talk about. By the way, allow me to divert 1 minute. We have Imiloa Astronomy Center in Hilo, which is just down the street from our base facility, where this is quite unique. 42U, WWT, and Cyber Canoe are all working, thanks to my colleague Yuko Kakazu, who has been working with Imiloa Astronomy Center, and upload our own data to the system. So please come check out. All right, so, okay. Then, tagging along what Shirasaki-san just showed, let me start from this one, HD 142527. This is from Subaru telescope, the protoplanetary disk comics from the cooled mid-infrared camera and spectrograph. That's what you're looking at. ALMA data showed two, basically ring structure, and the comics, which is warm dust, shows this kind of warmer side and cooler side. Okay, so my eyesight. Come on. And I have to mention this, okay? Talking about citizen science, and then I do something small on top of the rooftop of the Subaru building. And also, okay, Satoshi did not mention this, but HSC is contributing a lot for the better understanding of our solar system. The solar system as we know it, probably you can think of as far as Neptune's orbit. But there are many things out there, including Planet 9. So probably I should get ready for the press release, big press release pretty soon. This is probably the second year of the 5-year search by Dr. Mike Brown's group. And there are at least 2 more groups searching Planet 9. And we have this convenient tool to utilize when we do the press release. Okay, so talk about this one. This is Subaru telescope enclosure, but this is not. It is not the reason that I show this picture. Look at the rooftop of this control building, and there are small dots shining, and 2 of them are small camera systems. One is Takehiko Sato's group's camera. Where is Kaoru-san? Yeah, okay. So she is also part of this, she's leading this program called ICANN, a small camera system distributed throughout the globe so that somewhere, one of the cameras, one of a few cameras can be in the night side. So you can use it during the classroom time, wherever on Earth. It looks like this one, R2D2 we call. Installation was done by Science Museum staff because it's round roof. And off the have to have safety harnesses. And as I speak, probably today the condition of Mauna Kea is like this. And the communication is down. The power is down, so I cannot show you what it looks like right now. Sample images from ICANN is like this. This covers probably 1 constellation over Mauna Kea, so it is quite useful when you are using the image for the classroom work. Then there is another one, Todai Adachi camera. This was built by Todai University of Tokyo Group and funded by Adachi Galaxy Group. So when you go visit Adachi Galaxy tomorrow or the day after, they show the picture from this camera. Like ICANN, this Todai Adachi camera are located at least 3 locations on Earth. Hiramatsu-san, you also have both ICANN and Todai Adachi camera, right? No? Ouch. Okay, so, Todai Adachi camera is very, very simple fisheye camera. Simple is very important because then every night it's been working. And Adachi City has this log. And, okay, when the moon is out, the enclosure of Subaru telescope is like this. It's shining. And sometimes you see this kind of phenomena. And that's the beauty of real sky. Sometimes something shows up, and you feel, wow. Or if nothing else goes on, you can give some kind of title. Yeah. The moon is out, that means a bright night, and the infrared observations are going on. And for the infrared observations, in order to get to the high spatial resolution, astronomers start to use the laser guide star to do a good adaptive optics to compensate for the image blurry from the atmosphere. So you can tell this is infrared observations looking at not the galactic center, but sometimes the 3 or 4 lasers converge on the galactic center in May, especially. And I was supposed to show the blue sky of Mauna Kea today, but this was about 2 hours ago. And this is another aspect of the ground-based facilities. And it's real, really real. And the power outage might be affecting the transmission from here. And the fisheye camera is covered with ice. That's not icicles, okay? And this is Subaru Telescope's parking lot. During this kind of severe snowstorm, right now, the snowplow just made it up to the summit. And then our day crews go up and clear the entrance and work on instruments. So I hope tonight we will be able to see the sky again. This is from University of Hawaii's all sky camera. And again, you can give it a good caption. 2 lasers and 1 big Cheshire cat smile. So that kind of, well, even though this is only black and white image, you can think of many things, what's going on in the world, I mean, in the sky, over the sky. And that will intrigue some kids in the classrooms or evoke conversation amongst the family members. Then I think about the visualization of the large-scale data. That's my message. Oh, am I too early? Oh, okay. In that case, okay, so that's me. But this is probably the best image that I have. Oh, I know why. Ooh, this is too dark. Well, we have YouTube channel Subaru Telescope has, and one of them, the videos show this Geminid from 2 years ago to 3 years ago. Okay, so in that case, let me start from here. My other colleague in my team, Dr. Hideaki Fujiwara, compiled and created this video clip. You can see the air glow. And, in good season, you can see zodiacal light as well. And the importance of connecting the real sky with what's going on the mountain, I need to talk to the people in the local community, which is very, very important. Our press release or outreach effort, it's not only for the Japanese taxpayers. Subaru Telescope is funded by the Japanese government, but also it is important for the survival of our telescope or continued operation. We need to talk to and gain the understandings of the people in the local community, because our lead of the land where the telescope sits on is until 2033, and we need to renew. We want to get a renewal. For that, understanding from the local community is very, very important. And that is why we strive to provide information not only in Japanese, but also in English. And this, well, you don't have to use any language. This image should show the beauty of that mountain, and we can share many things based on that kind of image. Okay, so that's what I wanted to share with you today.
Many thanks. Right. Saiko. So, any questions for Saiko?
Do the Planet 9 press release. I would like it to do it in Hawaii, California time. I'm referring to Holy Cow release, which was a joint press release amongst many, many institutions throughout the globe. Since it was led by Lars group, it was 2 a.m. in Hawaii. So for Planet 9, I would like to do it 2 p.m. in Hawaii.
I agree. We should make the Earth flat. It's much easier. It's all this time zone nonsense. But it is true. And I have to say, Masaki also often sacrifices himself for the telecons in the middle of the night to reach across the globe. But it's also beautiful in a sense, right?
Yes.
That we're working together as a community and that we really collaborate.
Yeah.
Anyway, questions? Masaki?
Sorry, not question, but my comments. I just said the camera in Alma is broken, but the broken camera is the ICANN camera is broken.
Yeah.
And the Adachi camera is at the top of Chahananto. It's not Alma site, but Tokyo Atacama Observatory site. So I think it's still working. And also Alma provides a new nearly real-time all-sky camera. This is a huge effort from the ESO, and we contributed to the setting of this all-sky camera. So basically every hour, that camera provides a full sky image from the Alma 5,000 meter site. Resolution, do you know, Lars? It's very high resolution.
I can even show it. Unless my computer doesn't like. No. No, it doesn't. It's a 4K resolution image, very, very deep, and also it's actually probably the only real 4K image I've ever seen, because normally you have a sort of DSLR camera with all the deficiencies of the lenses and things, but this is a 10K image downsampled to 4K, so it's very nice. Every hour, yeah. Also during the night, and it goes fairly deep, somewhat deeper than what you saw here. At the moment at Alma, it's very, very bad weather, so we'd actually better not show it. You know, you're at the top of 5,000 meters, lowest precipitation in the world, and then you have these rolling clouds and rain and snow, and yeah, but that's how it is. Good, so we're ready for the next talk, unless there are any more comments. Akira Miura-san. NAOJ? No, sorry. We're talking Institute of Space and Astronautical Science, JAXA. Visualization of space science data using the data archives at ISAS.
Thank you very much. Good morning, everybody. I'm Akira Miura from the Institute of Space and Astronautical Science. that is, the institute was first established in 1964. It was born before I was born. So, and the nickname is ISAS, ISAS. And now it is a part of Japan Aerospace Exploration Agency. And now ISAS has a system named DART, which is Data Archives and Transmission System. It was established in 1997. DART contains many kinds of data, for example, astrophysics, solar physics, solar terrestrial physics, lunar and planetary science, and space environment utilization, and so many. So I'd like to introduce several topics of DART and relating visualization services. Actually, I'm not the expert of this system, so please don't ask me the detail of the system. I'm mainly working on the visualization, mainly using these data. This is the home page of DART. And for example, astrophysics category, there are so many data of the satellites. Today, I introduced the data of Suzaku. This is the X-ray astronomy satellite. And also, ASCA is also X-ray astronomy satellite. And Akari, this is infrared astronomy satellite. Well, this doesn't include the image, so I selected a nice one. This is the mascot of Akari. This is the actual data of Akari. Sample of all sky image data. Okay. Oh, sorry. Well, this is another example of data of Akari. It's high resolution data, so you can zoom up. Well, like this. Okay, let's continue. And this is an example of a visualization service named JUDO, JAXA Universe Data Oriented, JUDO. Well, don't think about the kind of sports. And another visualization service named UDON, Universe via Darts Online. Don't think about the noodle. Probably named after the noodle. Okay, this is an example. Oh. You can browse the data of, for example, Suzaku, ASCA, and other satellites, and click the image, and also you can examine the data. And today I tried to demonstration udon, but it seems it has something wrong. So today I show just the snapshot. Next category, as for solar system science, it has some subcategories. In the category of solar physics, this is Hinode currently observing the sun. An example of the movie. It is a movie of solar eclipse last year. And also, Yoko was observed the sun. This is sample images. Okay. And you can see, you can browse the data using the interface named Cosmic Calendar. This is a service of browsing data, monthly data, and also you can browse daily data. Next category is solar terrestrial physics. In this category, I prepared a data of Raimei. Raimei observes aurora around something. Most of them are low-resolution data, but Raimei observed many kinds of aurora. And you can also browse that data using the Cosmic Calendar. Okay, next one is... next category is lunar and planetary science. Recent topics, one of the recent topics is Hayabusa 2. Well, this is the mascot. As for Hayabusa 2, this is images of during the Earth swing by. Okay. And as for Hayabusa, thanks to Carter-san, many interesting demonstration was presented yesterday. So I have, this is mascot of Hayabusa and Itokawa and so on. I have another visualization service. This is Flow, field of view visualizer. Flow itself is a library to visualization, library to visualize the field of view of onboard cameras. But this is an example of the application. You can see the field of view of the onboard camera. This example is Hayabusa's Amica, onboard camera named Amica. Another day's example. And real images are presented using, provided using the Cosmic Calendar. And also you can browse daily image. And okay, skip this one. And as for Selene, or also known as Kaguya, there are 3D GIS, three-dimensional visualizer, and high-definition theater. This is just an example. Oh. And many other data are provided through DART and 3D visualizer, and there are so many services provided by DART. So, okay, I skipped this one. Oh, just visit the site of DART. DART is mainly intended for academic use, and Space Science Showcase is provided by another server, which includes Cosmic Calendar. This is the latter is rather for outreach or public relations. And as for ongoing works relating to the visualization, thanks to the organizer, I have another slot this afternoon. So, this movie contains compilation of short clips for full dome screening. So, just visit 4D2U this afternoon. Well, that's all. Thank you very much.
Thank you, thank you. I think I know which questions are coming now, but let's see. Anyone? Questions? Then I will ask it. So what about licensing? That has been the big debate for quite a while, and I think we have a big community here who is eager to use all the amazing things that are coming, the HD movies from the moon and all these things.
It's a difficult question.
Sorry, I had to ask.
Probably you can use the movie for academic usage, but if you use for commercial or something, I'm not sure. Sorry.
No, I know it's a problem, but also you have probably people here who charge an entrance fee for letting people into the planetariums. That doesn't mean they actually make money, that's clear, but it is a kind of commercial use. So there is this issue with the typical Creative Commons non-commercial licenses that it's not very easy for planetarians to use. Nevertheless, let's mention it to you yet again, and hope we can somehow nudge things along, because there are so many fantastic resources coming from JAXA.
Thank you very much.
Let's have some more questions. Maybe one or two while Ben is setting up.
One comment. On the Hypsats fits file, if you want to use those fits file, please pay attention about the illegal format. I already mentioned that to the author, those fits files are not compliant to FITS standard, so I strongly require please create FITS standard compliant data. So if you read by AstroPy, you cannot read some headers, so please take care.
Thank you very much.
Okay, let's thank the speaker again. Thank you.
Thank you.
And now over to Ben Emmons, who will talk about LSST with LSST as data in Day2 Dome.
Thank you very much. I want to thank Mark and IPS for organizing this event. I want to also thank NAOJ for hosting the event, and for all of you for coming and those who are on the telecon. It's great to have this participation. My name is Ben Emmons. I'm the Project Manager for Education and Public Outreach for LSST, the Large Synoptic Survey Telescope. My slides can be found with that link in the bottom right. So if you find that it's a little difficult to see in the background, feel free to load that or save the PDF for later viewing. So yesterday we heard a lot about the dome. We heard about planetariums, we heard about software in planetariums, we talked a lot about planetariums. Today, we talked a lot about data on a website, data from a science mission, data that is exposed to the public. My goal is to combine those two, to talk about the connection between those in the context of LSST. And so to start off with, let's talk about data, because those who are familiar with LSST know there's a lot of data with LSST. The form and function of the telescope is somewhat similar to HSC in that you have a mirror system. It is unique in that LSST has 3 mirrors. It's large, 8.4 meters. It's got a 3.2 gigapixel camera, so HSC is 1 gigapixel, 3.2 gigapixel for LSST. What that means is the telescope is going to capture about 15 terabytes of data a night. And it's going to do that every day for 10 years. So when you add up all of that data, you're looking at about half an exabyte of data. That's the order of magnitude past petabytes. That's a lot of data. There is a fraction of that data that has been allocated for public use, and that's where my department comes in. We get to take a subsection of that data and expose it to the public and allow them to use it. And it equates to about 2.2 petabytes of data a year. And we are going to be in classrooms. We are going to expose this data for citizen science. We are going to be taking this out into the general public with a web portal similar to a lot of the portals you've seen today. But I wanted to focus my comments today specifically on our goals for planetariums, the dome, since that's the focus of this conference. So our hope is to reach out to kind of a broad audience. Think about visitors coming into a planetarium. You've got a diverse audience. We want to be able to keep it relevant. People keep going back to planetariums for reasons because they have an experience that they feel like they're having a connection with the universe and they are in the midst of brilliant scientists that inspire them. And so this is kind of where we want LSST to play a part. We also want to know that we're doing the right things for the right reasons. A lot of times you build something because you think this is cool or this is what you want, and then you get to the finish line and nobody uses it, or they don't use it as much as you thought. And there's that moment of like heartbreak, right? Like I just poured my heart and soul into this for the last how many years, and you know, it's just a little blip on the analytics. And so we want to make sure that we're creating things that will actually be used and will be useful for our audiences. So what we did is we hired a contract firm that goes out and does needs assessment. And they went out and talked to a number of people in the planetarium space and museum science center space. Now, if you don't see your name up there, it wasn't because we didn't feel you were worthy, it's because we only had a small number of people and a small amount of time to work with. So my apologies that we couldn't capture everyone's input, but if you have input, we would love to hear from you. So I'm going to share some of the findings from this, but feel free to reach out to me and say, you know, they missed some other key point that I think is important. Please let me tell you about it. We also tried to capture a variety of different kinds of centers and planetariums. So if you look around, you're probably looking at, for at least the international participants, really big planetariums that have a large budget. Why? Because they can send people to Japan. you probably aren't seeing representatives of those small high school planetariums or those inflatable planetariums or those little planetariums on community college campuses. You're not finding those medium range planetariums that have a small staff that don't have a lot of resources available to them. We want to make sure that we are reaching out and meeting their needs and not just the really big planetariums with lots of resources and staff. And finally, because LSST is being built in Chile, we want to be very conscious of the needs of the Chilean public. And initially, I went in somewhat naive thinking, oh, you just translate the content, and there it is. It doesn't work that way. There's a lot of very specific needs from the Chilean people that we have to take into consideration. So I'm not going to go through all of this because the slides are available and you can read through it, but bottom line, big planetariums, lots of staff, lots of resources. They love to dig into the tools. This is what gets Mark up in the morning. He loves to try out new tools. It's like a candy store for him, right? He's just like trying this, trying that, seeing what works. He's got a whole bunch of staff, and this is just what they live and breathe. They love it. And guess what? They do amazing things. They've put together some amazing resources. And when you do something like that, what's the first thing that you want to do? You want to share it. And that's one of the big pain points that the larger planetariums are finding, is that they do have all these resources, they want to help out, they want to share it, but because of all this fracturing of the different vendors and the different formats, they can't. And that's something that I'm hoping that this community can help solve. When I speak of different formats, I'm also referring to dome casting, and we heard about that yesterday. It's an exciting opportunity that we want to look into. Smaller staff planetariums, small to medium, what they find is that a lot of times they're dealing with somewhat aged projector systems, or maybe they're on a software system that isn't one of the top 5, and so they're very limited in what they have. They don't have the staff to be able to do a lot of this creation work themselves, and so they're really at the mercy of what the community shares. And then finally, it's not just enough to go and find some pretty picture off the web. They need to know what they're talking to. And a lot of these smaller planetariums, they don't have the, say, resources maybe to hire the Lucianne Walkowitzes of the world that are just like incredible superstars in the EPO space. A lot of them are volunteers. A lot of these people work at maybe a campus that's associated with the planetarium. And so they need a little bit more help in talking about the context of what this material is that they're about to show on the screen. They feel like they would like a little bit more assistance in being empowered to speak to what they're about to show. And finally, the Chileans, it turns out that one of the things that their audience prefers that's unique to American audiences that we've discovered is that they're very hands-on. They really like to interact. It's a lot more exhibit focused rather than planetarium show. And when there is something that's like a show, they want it to be immersive, whether that's through a projection system that makes them feel like they're inside of it, or if they have like live audience discussions. There's a very strong need for a personal connection. Part of the reason is that many people in Chile don't have the opportunity to go to a planetarium more than once or twice in their lives. This is like going to Disneyland, right? For those of us here. This is a big deal. This is like a once-in-a-lifetime thing. And so it's more than just come in, sit down, watch a show, and leave. It has to be an experience. And you remember things you touch. You remember that conversation you had. You remember those experiences that are a little bit more tangible. Okay, so what is LSST planning to do? Well, if there are a whole bunch of different standards and formats out there, that's a challenge for us. If every single one of these science museums and planetariums have different floor spaces, that's difficult. If we're talking about all sorts of different skill levels in what we can present to the public and them find useful, and finally, if we have all sorts of different hardware, digital projection systems, analog, you've got different walls, touch tables, all sorts of things, we finally decided for LSST to bring it down to the lowest common denominator. Media assets. And so what we are planning to do is to leverage this data to dome concept that has been proposed by Lars and by the IPS in creating this set of multimedia assets in a way that hopefully could be easily adopted and consumed into each one of the planetarium software, different types of software. The other thing that we're hoping to do, in addition to providing this media, is expose something that's unique to LSST, which is our alert stream. And so for those of you who aren't familiar, in addition to the optical data that the telescope is receiving every night, it's taking that optical data and doing differencing, and it's discovering what changed. And each one of those changes is an alert. And we are expecting on the order of 10 million alerts a night. That's a lot of data. There's a lot of changes that's happening in the universe. You want to share that dynamic universe with your audience. You want them to feel like, I'm not just looking up the night sky, it's the same thing every time, every night. Or if I'm alive for 1 billion years, I'll see something change. You want to give them that feeling that, no, everything is happening like right now. There's a supernova occurring. Right now there's an asteroid we never detected that we just found. You want to share that dynamic experience, but you can't overwhelm them, right? If you show 10 million dots on a planetarium, it doesn't mean anything. And so we need to figure out a way to make 10 million or even 1 million, more consumable at the planetarium level. And so that's what we're hoping to hear from you with your experience in the planetarium, with your experience with your audiences. How can you take the amount of data that we anticipate with LSST, how can it be useful for you? And what can we do? Because we have a number of years during construction where we can build it and tailor the output to your needs, but we need to hear those needs now so we can start building and preparing for it. So thank you.
That was really very interesting. I had somehow also reached more or less the same conclusions, that over-planning for the audiences is also, it's very difficult, and giving people a more diverse choice will help in the long run. It is a very diverse community. Anyway, questions or comments for Ben? $10 million events in a night. That's a lot of events.
Thanks, Ben. That was a really great presentation. And one of the great things about LSST is that so much planning has gone into place, and actually looking at what the audience needs and thinking about the product that a lot of projects don't have the opportunity to do. One request, and actually I think a request for a lot of the speakers, or all the speakers almost, is that this information could be used by a lot of groups, and if you would consider writing an article for the planetarium, that would be much appreciated.
That's a great point.
Or Cap Journal, but something.
Can you publish it in both?
Sure. We'll
So-
take anything.
This is more an observation than anything. I think that, to me, this, as I kind of indicated yesterday, this strikes me as a sea change in terms of how we talk about these topics, because it's this very dynamic and constantly changing topic now. And it would be great to think about, first of all, going back to this idea of community, building community, and community practice around telling these kinds of stories and figuring out what kind of stories we're going to try to tell with these data. But also, how can we road test some of this? And so, dark energy survey kind of stuff, or things that are kind of the closest parallels that we have. It would be great to sort of use those as a way of trying out some ideas on how we talk about these data and how we lay the groundwork for the deluge that LSST will bring.
Totally agree. Fortunately, many of the data missions that are coming up, or science missions, are kind of those baby steps towards that larger data set. But you're right, it is a sea change. This is a significant paradigm shift in the amount of data and how to make it useful. And I've just talked about planetariums. There's a whole other set of conversations about how to make it useful for teachers, for citizen scientists, and that sort of thing. But you're right, this is a huge sea change that we need to prepare for now.
There's a parallel with all the data that's being collected about us. So there's a data parallel that's outside of astronomy that's really a source of anxiety for a lot of people. And in a way, recognizing that there are parallels between these, I think could help us sort of understand how our audiences are going to respond to it as well.
All right, thank you, everyone.
Yeah, thanks. Break time. Okay, so we're ready here. It's 11 o'clock in Tokyo, Japan. I can only guess what time it is in Colombia, early morning or?
It's 9.
9 o'clock, okay. And we have Carlos Molina, who was hosting the CAP 2016 conference in Medellin. And Carlos will talk about Helios, a new show, Helios Tales from the Solar Neighborhood. If you could ask for the slides to be moved forward, then we will show them on the screen if there are slides. Other slides? Yeah, we have the slides. All right, we're ready to go.
Okay, good night for all. I'm very happy to be here with you this night. This night for me, this day for you. I'd like to talk about our recent production in Planetarium of Colombia. It's a homemade show. It's a big effort to put contents on our dome with the sense of the context, of the regional context. It's true and a new experience for us because we don't have a big center for production, for produce contents for full dome, but I think that we are in the right way, and I would like to share some of the behind the scenes of these shows. So let me talk about the people that work in Helios. Well, I'm the director of the full-dome show, but the main people that was involved with this show was David Toro and Felipe Orozco, that are very creative people here in Medellin. I'm not more in the Planetarium of Medellin, in the University of Antioquia, but David and Felipe are in the Planetarium and are working a lot now. Next slide, please. Well, Helios is a production, Alca production. It's a 4K full-dome show. It's a 24-minute show. It's a new experiment for us because we are trying to add to the tradition of digital scale to visualization free resources for create 3D sequences, and we did the product. So we use Blender mainly for create these scenarios in these shows. In this show, and we are producing this show for 1.5 years. In fact, last Saturday we launched the show here in Medellin, and was very successful. Next slide, please. So, the story of Helios. The story of Helios is the name, first of all, it's an allegory to the journey of the Greek god Helios, that is the god of the sun, but the sky. And our proposal is an interpretation of this journey around the solar system. Our first thing is a view of traditional cosmic view of the universe since the Earth, and we begin the show in the middle of the sea in a little boat. And this reference is to create the image of the knowledge, the great knowledge that is inspired in the universe. So the first step is in the sea, but after that we go to the center of the sun, to the very close center of the sun, in the core of the sun, and we recreate, in fact, the beginning of the solar system in one scene, showing all the primitive nebula, using just 3D models with Blender. After that, we go to the present. Next, please. We go to the present to see the updated vision of the solar system that is provided for the most recent data provided for new frontiers, for example, for Dawn mission and other mission of NASA, ESA. And we take this information to put it on service of the people. And we try to create landscapes of these planets. We know that many planets don't have proper images to show for the public. So it was a kind of adventure to try to show for the people how could be here in one planet or one moon in the solar system. And we used maps for elevation data and artistic views for show this kind of landscapes. Next, please. So here you can see a print screen of first scene is in the middle of the ocean, as I said before. In the left side is the boat. Was created with Blender, and all the image, the sea and the mountains were created with Blender. The right side is the final composition for that scene. And you can see the Milky Way, the hills of Milky Way, and we use like a background for the beginning of the story. All this production, the 3D, all that work produced with Blender, in fact. Next. Now you can see a short video. We use the digital sky objects, but we use through the amplified information with Blender, showing some the images of the mission that explored Mars in the past. And after that, we try to recreate real panorama or landscape in Mars using the elevation maps extracted by NASA. So this is the Marineris Canyon, Mars, and you can see the elevation of the atmosphere in Mars. It's an approximation, but we want to the people in fact feel in Mars. That is our proposal. Okay, next. This is a short film series. The object was created with the images of the Dawn mission. The particles around is a recreation of the particles in the asteroid belt. So the video was created almost all with these textures of the Dawn mission. So this is not just the position, but the approximated view of cities. Next, please. Okay, we used additionally a video to recreate the appearance of Jupiter. We covered the small ball that you can see the lever in the left side. We covered a video, and we put additionally a model of Juno mission, because our proposal is that this show could be the show for the new generation in medicine. Many of us grow with the memories of the Voyager, beautiful Voyager images. But we want to show for people the new stuff in exploration in the solar system. So this is an image of Jupiter, and a sequence of Jupiter and Juno created with Blender tools. Next, please. And for Venus, we use the radar vision map of the Venus for the approximation, And after that, we try to give the sensation of immersion. A planet traveling around the clouds. And finally, we going to the planet, to the surface of the planet. We create a landscape. It's not obviously a true image of views, but we want to the people things about the life, about the feeling that experiment a planet with a very different atmosphere compared with the Earth, and compared to the size of the rotation direction of the planet for expand the vision of the program these topics. Next, please. And maybe you can recognize this image. Was an image from Luis Calzado, I think. It's an artistic representation of Triton, and this image was very inspiring for us because we are trying to see the reference about this place. We want to show the solar system, not just like planets, but a place that you can see, that you can explore, and you can feel, and try to stimulate the imagination of the kids, to think about the next generation of exploration of space. So use this beautiful image. Next, please. We create this sequence of Triton. We put some things important in this image, like the albedo. The planet was composition too in planetary using the apparent distance to the sun, and you can see the Neptune planet close to this moon, and we tend to put all this in the context of the limit of the solar system before the Kuiper cloud. So this is a little bit of our production use in planetary modeling. We use a lot of brick material, brick content to construct a new version for the solar system, and a paid version for the solar system. And we are very interested to share this kind of knowledge that we gain in this process. Next, please. So thanks a lot for these little minutes. And if you have any question, I'm truthful to reply. Thanks a lot.
Many thanks, Carlos. First question I can ask, how will you distribute the show? Will it be for sale or will it be for free available?
Okay, initially I don't have a good but for that, because I'm not working or in planetary modeling, but I think they are interested to distribute for the community for low cost. Not a free license, but I think that a low cost. And it's an effort for the Latin American people. In principle, because our planetariums are very, let's say, not very rich planetarium. So we want to provide content for low-cost content. I think that this is the idea of the planetarium.
Okay.
But at the end of these clips, I think that we can distribute for the community for free some of the clips of the show.
Okay, that sounds good. Thanks. Are there any other questions for Carlos? Let's see if you can hear Mark's question here.
Hi, Carlos. So having gone through a full production using mostly, well, digital sky, but other than that, open source software, do you have any comments? Do you think Blender is sufficient to for this type of activity? Making shows?
We use for almost all the background of the show, the digital sky resources. I think that 50%, but I think that the other 50% it's free resources like Blender, like images from the elevation maps from NASA, and other stuff that we don't make. It's able to combine the two modes of production. And in fact, we use this map for transform the original way that you see the planets, for example, in digital sky, and have an update view of the planets, in fact.
Thank you.
Thank you so much. Let's give Carlos a hand. And this worked really well, so yay for Skype. Better than expected. So yeah, thank you and have a nice day, Colombia.
Okay.
Next up is everyone's favorite, Pedro Russo, formerly of the Portugal, now has become international European, residing in the Netherlands. And Pedro will talk about public access to research data.
Thank you, Lars. And it seems that the Netherlands is having elections in 15th of March. I don't know about that European anymore, but hopefully yes. Well, like Lars, I said, it's not, it was there before? Yeah. Is it working? Right. So, like Lars said, I'm based in Leiden University in the Netherlands, and I think it was really nice to be here this morning and to hear a lot of things that I've been thinking about, this idea of how can we make sure that the research data is more accessible to the public, and how can we get the public more engaged with the data. And I think there's a lot of thoughts on that. And more in line with the title of this own workshop, I think the title should be Data to People. How can we really bring data and people together? And what kind of considerations we need to make at this particular moment. So I think we all agree that in astronomy, we are way beyond this idea of big data. We are really talking about mega data. All these big projects that we are talking about will be produce huge amounts of data that we still don't have technology how to handle this data, which for me is fascinating. How can we convince policymakers to provide money for something that we don't know if it's going to work or not in terms of data handling? But still very impressive. For example, the square kilometer array will produce 10 times the current global internet traffic when it will be working, which is mind-blowing. And will produce a day what they call 1 exabyte, 1 billion of gigabytes per day. There's no way to save, to store, and even to process that data, all that data. So the data, they need to find new ways how to process this data. The same with the space missions. Of course, bandwidth for space missions are limited, but also increasing rapidly. For example, the upcoming mission from the European Space Agency, Euclid, will produce 850 gigabytes of data per day. And over 10 years, they will produce 10 petabytes of data. It's also a large amount of data they're going to produce daily. And astronomers, the community, needs really to find ways to work with this data. The astronomy scientific output is also increasing dramatically. This is a plot for AstroPH, the archive, and since 2009 they split them in different subsections of AstroPH because it became so popular. And now we are talking about around 35 to 40 new astronomy research articles per day. And like was mentioned yesterday, around 80% of them do make news. They write press releases about discoveries, and there's also public outreach data that is released through these press releases. It's quite incredible, 40 new astronomy research articles per day. Maya Dillon, some 2 years ago, more or less, she wrote the interesting article on The Guardian about what are the challenges for astronomy in terms of big data. And of course he talks about this, how can we visualize better these large astronomical data sets? How can we create better algorithms to process this data? And how we can really use the machine learning. And these methodologies of machine learning is something that, of course, a lot of our colleagues, data scientists, are working in, and they really hope to get some interesting results. But she raises a very important point. How can we make sure that the society is engaged with these astronomical data sets? What should we be doing for that? And I don't think we as a community, we have an answer for that. Of course, also the policy, the governmental agencies, the policymakers are setting new policies about this idea of open science, access to data, how can we make our data freely available to the people, how society can use this data. And also last year, the European Commission released an interesting report about open science, open innovation, open to the world, and really is trying to encourage every single research community, but also different sectors of society in general, to make their data freely available so everyone can use and everyone can decide what to do with the data. That's kind of this imperative of making big data publicly accessible on open science. And of course, this will include not only the data to be available to download and be readable, but also we need to ensure the long-term preservation of some of these data, and we need to provide some type of layer of metadata that other people know how to work with this data. So there's a lot of things that data communities really need to consider, and the policymakers will be pushing more and more and more in that direction. I think there's no doubt about that, since most of the data is produced by money coming from the taxpayers. But what are really the implications for education and public outreach? If we look at the data processing cycle, from collecting, processing the data, providing some scientific outputs and interpretation, and even archiving and distributing, I think clearly there's a huge trends from the past decades on the citizen-driven data cycle. This idea that at the collecting level, we in astronomy community, we have been working with amateur astronomers to collect some of the data. The amateur telescopes and instruments are also increasing in terms of the quality and the accuracy and the data that we can use more and more data. In terms of processing, the type of at-home citizen science projects like SETI at Home being a pioneer, but of course more recently LHC at Home, etc. They've been really on the forefront of using personal computers to process some of these data. And of course, on the interpretation, Zooniverse type of citizen science, where we ask citizens, non-experts in astronomy, to analyze the data, to look at the galaxies and tell us what kind of shape do they have. And of course, there's a large number of these type of citizen science projects. And distributed learning, I think this is something that maybe we need to be a bit more innovative, but new distribution mechanisms like the one that Lars presented yesterday, I think can really be some of the small segments of what we expect in the future to bring this data and distribute them to more diverse networks. And of course, LSST also is already thinking quite ahead on trying to find new ways to distribute the data to reach different audiences. Interestingly, there's a lot of investment on these larger projects. For example, and this is talking from some of my colleagues, some of them in the office next door. Recently, they received 2 million euros to start what they call this Euclid Netherlands Science Data Center. It's just a data center to handling all the data. And from those 2 million euros that they received, there's no budget line for public engagement with this data. And for me, this is something to be concerned about. And we, astronomy communication, planetarium community should be aware of these things and really pushing as much as we can to make sure that we find ways to the public be able to access and work and experience the data that we are creating in modern astronomy. So I'll be talking with them after this talk. So also when we look at the data processing levels, we talk about, let's say, two main levels in research, and we can even talk a level P for public outreach. And it's really the idea that, of course, the telescopes will collect raw data, the instrument, depending on the characteristic of the instrument, the data will be calibrated. The data will be added the physical information where the pixels will have a physical component, and then we make the data that is understandable and usable by non-experts. And I'd say that all the press release images, they will fall in this level P that we want to call it. So this is pretty much that what will be the target audience for each of these these different levels. Of course, level 0 and level 1 usually just the engineers and the instrument scientists can really understand. Then of course level 2, the specific research community and some of the communities, including the planetarium community, can work with that data and been working with that data. But the public will not be able to understand or even work with that data. So we need to make really, is a new level for this data processing. So it would be quite interesting to understand what will be the cost benefit to include this new layer of processing at early stages of the data processing pipeline. When you produce raw data, this level 1, level 2, and level public, what would be really the cost benefit to at a very early, at as early as possible, to include this new level on the processing. And I think Lars also touched this a bit, and this of course is a different topic, is what is the current public access to outreach images. And sorry that the image is a bit, but hopefully there you can see it a bit better. But we did a kind of, based on the study that Lars published on CAP Journal recently, we look at the different organizations around the globe and really trying to find what is the current status of the access to data, access to public outreach images. These are public images for press releases so newspapers can use. And you can see that there's some organizations that are being used in the Creative Commons BY, the attribution 1, but still a lot of organizations either don't make it very clear, so newspapers, movie producers, textbook publishers will not know how to use the images, or some of them don't allow what we call commercial products. That might be an issue for organizations like planetariums, because the planetariums do use some of these images for commercials. They charge entry tickets. So should we need to have new guidelines on when we make public images, should we always ask to have at least attribution and allow people to really create commercial products? That's something that we should definitely discuss. Also, based on Lars' article, there's a decision tree that you can follow when you produce these images and what kind of image, kind of license you want to use. So, some recommendations from very personal recommendations. I think public engagement with data in terms of these large projects should not be an afterthought, should be included from the beginning of when we decide to start talking about data in missions and new observatories. I think the scientific community and the data community in astronomy needs to work closely with the EPO community during the planning phases. We need to allocate resources on the data processing budgets for producing public data. And of course, I think we should make all the data available free and under Creative Commons license, an attribution license. And 2 years ago, we wrote this Mitaka declaration that I think you can find on the symposium book. So just to finish, in the last 2 minutes, we have been working a bit on this at Leiden Observatory, where I'm based. The first project that we've been working is based on our experience developing citizen science projects, especially on collecting data. This is a project that we developed in the Netherlands and in Europe. It's an add-on for the iPhone that pretty much you can scan the blue sky and and we can get the aerosol distribution based on that, and with different data points, we can produce very nice maps about the air pollution in the countries. I can explain a bit more the project during the coffee break if you are interested. Of course, this led to a research paper, and we had more than 3,000 people contributing to that paper. So based on this experience that we're developing, we are starting now what we call a citizen science lab. It's an incubation for citizen science projects. It's really focused in astronomy and space-based data, like environmental data, looking down with the satellites to Earth. And it's an incubation, like I said. We start with a call for ideas, so people can submit their own ideas. We select the best ideas. We try to involve some of the stakeholders, and we run a 1 week long workshop, hackathon style, that then a project should come out of that, and we provide a fellowship for up to a year for someone to fully focus on the project and develop this citizen science project. We already have the first one because of our experience in air quality, and we'll have the first week of the workshop in January 2018. So we are actually launching this only in September. Another project that we have been working as a master student actually with the TU Delft, the technology university in the Netherlands, we are looking at a way that we can make some of the eyepieces for amateur astronomers with a bit more augmented reality. Imagine that you're looking through the eyepiece and you look at the galaxy M31, and then you can have information about the galaxy real time. You can look at the data that is provided by other telescopes. So we are still on the prototype phase. It will be interesting to work with the Day2 Dome protocol or trying to get these latest discoveries so the amateur astronomers can go and look at the place where the new planetary image was found. So it's quite exciting. Of course, it's a student project, prototyping, but we are quite excited about this. Also, based on the Agatha-san conference in October 2015, we decided to hold a small symposium that we are still in preparation in September 2017, really trying to bring visitor centers, public observatories, and astronomy museums together in a small workshop, maybe up to 40 people, to discuss what are the synergies and best practices and resources that we can all use. But soon we're going to announce, and everyone in this workshop will receive the information. So to finish, and really just a provocative thought based on something that Kevin said a few months ago, I think this is an interesting question also for us to think about it. Which is the more important? Is expanding human knowledge or create more data, or bring humanity along when new knowledge is generated or when new data is generated? So I think this is a very interesting question, and we all should think about this, that we are involved in this field of astronomy communication. So thank you.
Thank you, Pedro. Deep questions? Ben?
Just as a point of information, on the Creative Commons and the licensing slide for LSST, I just wanted to make a note that LSST images are licensed under Creative Commons Attribution Share Alike 4.0.
It's good to hear. One more.
Thanks. I was on the website and trying to look. Of course, I didn't find any copyright statement, so I guess it will be open. But maybe we'll make it more clear. It will be easier. Okay. Good. Thanks.
One more question while Telina gets set up. Yeah, Ian.
I wonder if you could expand on the focus for the workshop in September that you're planning.
Sure, I can. So in October 2015, in this same place, NAOJ organized a workshop on the NAOJ Astronomy Museum, and they call it and related activities. And the idea was really to bring together people that have small astronomy museums, they have small visitor centers, or even public observatories, and really trying to bring that community together. I think it was found that there was no place for that community to come together. Of course, IPS brings the planetarium community from small domes to large domes. The people that have a small visitor center at their public observatory, there was no space for them to get together. That's why we decided to organize this small workshop to see if we can work together on developing exhibitions, activities for the public, learn from the experience of tour guides, etc. That's the idea.
All right, thank you. Thanks again to Pedro. Next up is Telina Hina Tigala.
Almost.
My Sri Lankan is not so good. So Telina will talk about Science Office. It's from Science Office, and we'll talk about the comet from Comet to Everyone's Screen.
Hi. Good morning. Yeah. So I'm from science. Some of you may know I actually work for a few different organizations, and I have been spending some time with Science of since last couple of months. And before I actually get into what I want to share in this workshop, yesterday there were some interesting comments from Lars and Mark and a few other people. And so I'm from Sri Lanka, and we have one planetarium which has been running for more than 10 years. Now it's almost about 20 years. And so yesterday comments actually reminded me of something a friend of mine said. So when I was in school studying, like high school, a friend of mine from US came down like for a holiday. And I took him to the planetarium, and because he was an amateur astronomer, and he really enjoyed it. It was in Sinhalese, the native language, but he really enjoyed it. It was an old projector. But then he visited me 10 years later, and we went back to the planetarium. And he said, obviously he enjoyed it. It's a really nice planetarium. But he said, 10 years later, it's the same speaker, same presentation, same data. So, and I didn't really notice, but he remembered that nothing has really changed. And this actually brings up, today I'm gonna show like three tools. Two of them are actually apps, and one of them is a screening today afternoon. And I just wanna highlight that these apps like these are really important for even the small scale planetarium. So there's a big need of actually shifting planetariums to online, so people have access to new data, new information that you can actually show right away. Otherwise, it's going to be. I'm sure that so many planetariums around the world is in the same situation, because it's very expensive to buy new programs, create new shows, and even the change to digital is super expensive. And yeah, so Science Office actually created a couple of years ago in 2008, and Pedro is actually a big part of it as well. And the basic idea is actually to show this science and visualize science to public. And we have been pretty much trying to visualize science for a long period. If you take a regular newspaper, you see images, but if you, at least in my experience, about 15 years ago, if you look at a newspaper, you see, any science article, rather astronomy articles, you actually see same image over and over in all the articles, because the content doesn't get updated and there's no visualization getting created. But now there's a big need on actually graphics and motion and videos and whatnot. And so Science Office actually plays a major part in creating things from motion graphics to data visualization softwares, web development, and so on. And yeah, just to give you guys an update, this is what we did last year. Yeah. So, out of these, some of the work we have done, I want to highlight two applications we worked on, and one of it called actually Where's Rosetta. Maybe some of you actually have used it or seen it. And so Where's Rosetta is an interactive 3D tool that we developed for European Space Agency. And Rosetta, I think in Europe, Rosetta was the most popular mission or the science activity. And so it actually helped to gain a lot of public attention, and this tool is a really great tool for public, even the students. And I have used it in a classroom in Sri Lanka. It's a really nice way to show people what we can do with actual data. And I'm just going to quickly take you through this tool. So when I mentioned that there's a need in the planetariums and even the museums moving towards an online platform, is to be able to use these sort of applications actually. And so Where's Rosetta is a tool where you can find pretty much the Rosetta's whole journey from start to end. And on the side you can actually, so you can play, and on the side you can stop and check the distance from the Earth, from the Sun, and the total accumulated distance as well. And also there are some important milestones Rosetta went through, and you can see these milestones on the side. And click on one of them, and it actually explains, gives some data, and where's the Rosetta at that moment. And so this is actually what's one of the interesting things having a tool like this is, now the places like ESA and the press actually makes a big announcement when the mission is launched, and even some of the milestones as well. But the biggest is when the mission is launched and the rocket is and the mission is actually closer to the asteroid, or once it actually landed on the comet. But the problem is, during this took actually a couple of years. But during this time, people are not aware of what's going on. There's no overview of the whole mission. And a tool like this helps people to get an idea how difficult this whole process is, how much knowledge and how much data and how much analysis, how much decision making going into the whole process. And tools like this is brilliant actually, especially in classrooms, and when you need to show students the process of a mission. And because mostly public here when a mission is launched and when it's actually successful or unsuccessful. And so Where's Rosetta helps to give you this overview look of the whole mission. And the other tool I wanted to show you is it's another one called View Rosetta's Comet. Sorry. Yeah, thanks. View Rosetta's Comet, and right. It's again an interactive tool, but this one is based on actual images taken from Rosetta's navigation camera. And this is also interesting because we talk a lot about using real science in classroom, real science in planetariums. And nowadays it's very important to show, because people sort of because of Hollywood influence on science, people sort of actually wonder if it is real or if it is actually manipulated, or what's real and what's not. And every time, one of the reasons is actually these citizen science projects are getting more famous, is because people get access to real data. And I work a lot with schools and teachers. And every time you actually introduce the real science in a classroom, they get excited, because you get to work with data, the same data scientists has been using. And that's something exciting. That's actually something inspirational for the kids. And so this tool uses the real data, the photo images taken by navigation camera. Let me quickly show you. And ESA actually developed quite a few classroom activities, including which things you can use in planetariums and science centers. And we actually used some of these, combining these two tools, which was very effective, because especially for, since I work mostly with students from developing countries, it's always nice to have something hands-on and something interactive as well. And so this is this tool actually allows you to do few things. You can actually click some areas, special regions of the so you can actually choose and study one part of the some parts of the comet, and it allows you to pretty much play with it as well. And also, if you zoom back, there are a few observation points where the spacecraft was actually when it was being photographed. And then you can see the photograph, and there's a link to the detailed photograph as well. So these tools allows you to these type of tools are very important in planetariums, because we are mostly working on I see there's a trend in developing more and more digital-based shows and like full dome type of things. Then we are sort of losing a large portion of planetariums and science centers around the world because they are not developed yet. So I think in order to imply these type of tools, we need to support more planetariums to make them online and allow them to actually use these type of tools. Otherwise, only really a small community of people will go with this full dome type of really big events. And lastly, I want to just quickly say that today afternoon we'll be screening the asteroid impact mission full dome video, and which is a short version, but you can download the full version online. Thank you.
Thank you, Sunil. So this show, is that available for free? Yeah. Oh, wow, cool. Any questions? I have a question if nobody else has. So the shape of the comet in the interactive application you have, does that come from the scientist?
Yes, it's actually from the. Sorry. Did you mean the second tool?
Yeah, the shape.
Yeah, it's from the Rosetta data itself.
I was just wondering if it was from the scientist or from that amateur astronomer who put together the shape.
No, it's from the ESA itself.
Okay. Any other questions?
So at the end, you brought up a really good point about the full community and small planetariums in the developing world. How do you imagine these kind of tools being used with, say, old optical planetarium in somewhere in the developing world? How would that work?
So, in my experience, actually, planetarium plays a key role in developing countries because you don't find many resources, and planetariums and most of the countries has one like planetarium, not a science center, and you get like thousands of students every year, and in Sri Lanka we get about 100,000 per year, and the thing is, this is, I think a planetarium is a stepping stone to do classroom activities later on, where if you link what you see in the planetarium with an activity which teachers can do later on in the classroom, that's very important, because one thing that I see missing is you go to a planetarium or science center, you actually see something, and that pretty much that's it. There's no follow-up, there's no continuation. And if the planetariums can provide more things like citizen science project, if you're from a developed country, or hands-on activities, if you're from a developing country, that would actually link and make it more useful, these visits.
All right, thank you. Last question from Carter.
That was a very good point. And one of the reasons we're making open space and doing it freely available was that we had started with UniView, making that freely available, and it quickly became a company. But we really had in mind places around the world that wanted to possibly download something for free, have it in their classroom in Africa, say, just as example, somewhere, anywhere. And but also, I think the point that Mark brings up is that okay, if you have limited resources, you can still get a cheap projector and just project some little area of interest like this onto a planetarium dome, but have that linkage back to schools, and I think that's really important. And so, and then making things to understand the three-dimensional nature of the universe available, I think is exciting for people to sort of understand that we do live in a three-dimensional universe, not just under a flat sky. So anyway, love to talk further. Thanks.
Yeah, sure, thanks.
All right, let's thank Thelina again. For our final talk before lunch, we have Jim Ching-Chuan Hung from Taiwan, talking about education and public outreach by Tam Planetarium in Taiwan. I did that nicely, huh?
Yeah, thank you. Thanks for IPS and NAOJ for inviting and coordinating this seminar and workshop. This is Jim from Taipei, a very small but kawaii, lovely island, very close to Japan. And you will see on the Google this time, today is Hina Matsuri Day, a Daughter's Day. Yeah. This reminds me the first time I visited Japan is also in March the 3rd. I saw many beautiful decorations here, and I made a decision. One day I have a daughter, I will inspire her to be an astronaut or as astronomer. But actually he study in mineralogy now. Yeah, but I think this is the day I have to thanks for Kasai-san and late Professor Shozo and Shozo-san because they held a star watching program to awareness to raise the awareness of light pollution around the Pacific Rim, and that's the first time I came to Japan to share the experience from Taipei in Taiwan. So this is the some paper inference for their efforts. At that time, I was just a college teaching assistant in the Central University, and you can see this is where I come from. And on the western rim, there's light pollution very heavy. And can you guess what this is? Yeah, fishing boat. Yeah, so seaside is not okay for the amateur and astronomer in Taiwan. So we tend to resort of National Park in central Taiwan, the Jade Mountain. So this is me showing the Mars image during the greatest opposition. Do you remember 2003? And this is after a whole night watching and picture taking. But the director informed me that the first thing in the morning, 8 o'clock, the reporter from newspaper will come in to see what we get last evening. So I had no time to take a rest facing the camera and microphone directly. This is why a planetarium in our museum, like weatherman or weather lady, we have to make a report last evening what we get. But the problem is Taiwan took some position in the international cooperation in the Marquea and in the Alma. So we want to make an effort to be a bridge to connect the amateur in Taiwan and star lovers to the professional one in ASIA, Institute of Astronomy and Astrophysics, Sinica. So we have to do some magazine. This is a quarterly, but we make it in a great effort to bi-monthly now from this year. And we have a Sunspot report every year sent to the Sunspot data. And I want to show you a little clip from our colleague here. This kanji, the Chinese character, means 60 years, but this film is made 10 years ago, so it will be 70 years now. And this is the Goto Sound Telescope since the very old planetarium. We have a Tenmondai Observatory in the old position, old location near Grand Hotel in Taipei. And we do that from that about 1940s, so it will be 70 years since then. But we got into the new museum and planetarium 20 years ago. So this is our colleague doing the sunspotting sketching every morning if the weather permits. So we will use their data to show the audience and visitor, even the school boys and girls from everywhere around Taipei, what we can see that day after the show, after the film, IMAX stone film or other film. And this is another simple, we will take it for view this afternoon. That's clips from the space weather and the sunspots. That's the last solar cycle, the cycle 24th. And we make some history origin, doing some space weather and the ancient people awareness of the change of the weather or something that don't awareness now. Okay. Apparently, our planetarium shows some program from ESO, NASA, even from Japan. So you will see Doraemon and Hidden Universe and Space Junk. But we put our efforts onto the space weather since we have a short clip from solar storms. Every star show duration is 15 minutes, but this film is too short, only about 30 minutes. So I have to do some programming on a 20-minute show to make a full length of that. And this is another effort we want to do that using UniView and After Effects. This is a dragon, very ancient symbol, one of the 4 symbols, dragon, phoenix, and turtle, and tiger. And this is not the picture taken by me, but I will show you what I do, because I'm an amateur star lover for picture taking. Let's see here. We often do the picture taking on the Central High Mountain around Taiwan and put it directly into the planetarium dome. And we using UniView to do the constellation line connection and the figures. And we would like to ask the favor from Kakaya-san using his great fine artwork to make this more beautiful. And you will see Orion and Taurus now turn into a tiger. Yeah, this is a very ancient Chinese legacy. And I took this. I only took 3 of the monsters, tiger, turtle, and the and phoenix. So I have 1 more animal to fulfill. That's the dragon. Okay, you will see the metropolitan light pollution on Taipei City. But people from everywhere around Taipei metropolitan will wonder if they can see Milky Way or not. So I will show you now what we show to the visitors, that even around the near mountain, the mountain near Taipei City, you can see Milky Way. But just before typhoon come in. Yeah. So before typhoon come in, there's cloud and fog everywhere on the mountain, but I took the Vega and Altair and Deneb, great summer triangle, to show the audience. And because we have only 10 minutes for visitors to listen to the introduction to the star show tonight, but we would make it 15 minutes length every Saturday evening using only microphone and laser pointer using Zeiss. We have Zeiss Mark 6 tilted dome. So during that 15-minute show, digital projector will be put aside. So people can enjoy the crisp image of the Zeiss. But they will feel somehow boring because they get used to very beautiful film and a sound and sound effect. So we will put some short clips about the constellation of about the story of constellation mythology, or the recently knowledge or news of the astronomical phenomena. This is the map of our site, and this is the tilted dome. We call IMAX Dome Theater before, but now IMAX is out from our theater, so we just call it Dome Theater or Planetarium. And this is the image I took from National Park in central Taiwan and put it in an advertisement showing where to get and what to see in the summer vacation. And this is the old picture, because we took this light box into a LG blender. The 3 screen blending together, and we can put anything new, even the data from organization all around the world into that before the audience came into the theater, they can see the preview here. So this is the traditional Zeiss show. This is a digital universe show. And pupils and students enjoy the competition of constellation recognition every year. We held a competition showing their ability to recognize all the 88 constellations on the sky. And they get prize, binoculars and trophy. And this is the show. We made more than a dozen of constellation program showing you. This is the first one with a teacher and a rabbit. And this rabbit is making out from the paper glasses in our 3D theater. We do it DIY for the recycling paper glasses. And this is from IPS, I mean IYA, IO, and professor. And we have the two figures by ourselves. There's Comet Tiger and the shooting star Meteor Cat. So this is a lady, and this is the brother, and they're doing the introduction of the constellation. And this is me bringing the students from community college to the southern Taiwan to see the Southern Cross. In Taipei, we can see the Southern Cross, but nearly without the southernest one. So we bring them to the high mountain in central Taiwan and the southern tip, Kentin. And this is the activity showing the summer camp, students and citizens doing that. Okay. Time limits, this is our homepage. And we're doing it in FB and the YouTube, everything we get free from the NASA and ESO. And we are intended to put our STAR program, I mean the planetarium program, eventually on this channel. So looking forward to it. Okay, data from professional is important, but data from amateur is also essential. So we periodically held amateur star photo exhibition, and we have just finished one during the beginning of February to the end of March, and we also have a lecture from the amateurs to inspire the interest from people, and they can contribute their beautiful photos to our program production. So we have to make a welcome party for them. So this is the last, but not the final clip. You know, this very popular several years ago. This is what my friends think I do. This is what my mom think I do. This is Hugo, Mr. Hugo from Zeiss. And the society I belong think I'm doing a 10. And my student in community college think I'm doing very fine, but I think I'm doing very lousy job. But actually, I have to do face in the program, Uniview and after event, day and night, so that's very terrible. Okay, thanks for IPS and NAOJ again. And this is me, but just doing the telescope businessman more than 25 years ago. This is the second time I visit Japan. So can you recognize this gentleman? Al Nagler. Al Nagler, the former president of Tel Aviv. You know the wide angle eyepiece, 2 inches. Okay, so this is the 45 centimeter telescope category made by Goto, Japan, and I doing the planetarium moon imaging time permits in the evening. And this is me on the Central Taiwan High Mountain using my lovely MID telescope. This is more than 30 years ago. And okay, this is Aurora and some image taken by me. I put it into the program. And feel free to contact with me if we can offer some shows in the future in English, and we would like to invite beautiful and great composition from all over the world, and every planetarian is welcome. Please contact me, and I need some help. Thank you very much, and see you.
Thank you so much. Is there a question or two?
Oh, I prepared some souvenir for you. A stereoscope view of our museum with beautiful sky, and I put it on the behind desk, and you will see the beautiful Milky Way in Taiwan and the beautiful museum. We call it Ferrero Rocher, the chocolate from Hong Kong, because our museum dome is like half bowl of the chocolate, and also the post-it sticker for you, and with a 3D postcard inside. Not so much left. Be quick.
Be quick.
Thank you.
Any questions? Carter.
Thank you. How many seats in your planetarium? How big is the dome?
The dome diameter is 25 meters in diameter and 304 seats. We used to have 325 because the former biggest planetarium in Taiwan is in Taichung, central Taiwan. They got 303 or 04. So our former director say we want to be the first. We want to be champions. So we produce 325. But that proves not work because we have very narrow control console at the behind. So when we review the digital one instead of the size, we make it bigger console and more comfortable. You know, a happy planetarian can say good things to the audience, and happy planetarian produce happy audience. So we would like to produce less audience seat, only to 304.
That's right, and happy planetarians need food. So,
Yeah.
With that in mind, it's time to go to lunch. I think it's same procedure as last time. Thank you, everyone. Thank you, Jim.
Thank you.
Okay, lunch break. Afternoon session start 1 o'clock. everyone. Time is now 1:05, but sorry, we have to a little more time delays. And we also plan to take group photo, and I planned before afternoon session, but it will be impossible. So we'd like to group photo at the 42U theater. Okay, sorry. Oh, about 5 minutes. We would like to start afternoon session because, as you know, we have to clean up this room till 3 o'clock. So we can't delay so much, so more. And we'd like to start 1:10, okay? 5 minutes. And please drink coffee and cookies and very interesting Japanese cookies there. No? Yesterday there was a very nice chocolate too, but today no chocolate here. Ladies and gentlemen, now we'd like to start afternoon session. First presenter is 武田さん、Asa Entertainment Corporation and National Astronomical Observatory of Japan. Title is Making Dome Movies from Astronomical Simulations with Large Number of Particles. Takeda-san, please.
Hello, I will talk about the way I made several 42 or other movies from astronomical simulation data. I'm afraid that my presentation is somewhat too technical ones, but let's start. Particle simulation is rather popular ones in astronomy. For example, simulation of galaxies or other proto-moon disk or dust aggregation in interstellar dust. My talk is about visualization or making movies from these simulation data, especially for dome movies. Often, these simulations use very large number of particles, very large number of particles. So, usual ray traced rendering of these particles is often too expensive and slow in many cases. So, I mainly used GPU rendering, OpenGL rendering. This rendering is commonly used for real-time graphic. For example, games or VR, etc. This GPU rendering has many limitations compared to commonly used ray-traced CGIs, but these techniques is much faster. I used homemade tools for particle rendering. This is based on OpenGL render. My intention, main purpose of my tool is rendering as fast as possible for many number of particles using these techniques. And with several tricks, such as preloading scene data beforehand or preparing scenes, backgrounds. In front, GPU render many particles. During the rendering time, often CPU is in idle state. So I multi-threadly prepared the next scene in such a idling time, so making scene rendering faster. With these tricks, at the most, we can render several 100 million particles. In ray-traced graphics, it is easy to make dome masters or full sphere equirectangular rendering. Most major software implements this rendering, but OpenGL rendering is not cannot render this wide screen image in single processes. So we must render several images. This is commonly used cube maps. Front, left, right, making images for different views and combine them to make full dome movies. It is very real-world sample of cube map, Google Street View or other full full screen views. And then render multiple images and combine these images to make full screen dome masters. In such a processes, two-pass rendering processes, discontinuity at the border can be a problem. My first talk is about how the source of the causes of these discontinuity and several solutions of these problems. At first, specular reflection can be a problem. Classical OpenGL rendering pipeline, specular calculation is not accurate one. This specular is calculated based on direction of camera. This is not accurate. It must be polygons positions and relative positions between polygons location and camera location should be used, but classical pipeline does not use them. So at the boundary, the direction of camera changes discontinuously. So this discontinuity happens. So solution is very simple. GLSL using shader languages, you can calculate these speculars in your own using your own functions. So changing rendering specular functions to accurate one, you can improve the problem of these specular ones. And next, an often used techniques is billboard ones. For example, gas particle, or this is used for gas particles or star particles with flares. For example, star particle and gas particles are expressed by these billboard textures like this. With these techniques, you can make movies with gas and stars like this. But of course, this can make discontinuity like this. And if you make the scene simply depending on direction of camera, discontinuity occurs. This is this can be very problematic. But solution is also very simple. You distribute these textures looking at the camera, not parallel to camera, but looking at the camera, then these discontinuity disappears. So this is also rather simple. And next, using billboard can speed up rendering. For example, this is a sample of particle image with many spheres. This image uses 240 polygons for spheres. And below is just using a textured billboard, sphere imaged billboard. In this way, you use only one polygons for particle. And there is no difference in appearance. But this is much too simple techniques, so there can be problem in dome rendering. For example, in dome screen, sunlit side and shaded side comes into view simultaneously. But if you use same texture in billboards, of course, you cannot draw sunlit and shaded images. So some contradiction occurs. Solution of this is rather somewhat complicated. We can use normal map techniques. normal map is color image with direction of normal is converted to RGB color, and then calculates the shading using the information of normal map. You can get complicated object with one single image. This monkey head is rendered on a single texture, but it reflects the position of light and shading. With these techniques, you can use billboard in dome screens. Sunlit side and shaded side can be rendered simultaneously. So it's very good techniques to fasten the renderings. And complicated object can be rendered by these techniques. You can make images and normal maps of complicated objects and distribute them. These popular character, Mixan, is all rendered in one polygons, but shading and lighting can be expressed. But of course, this is only an image, so they cannot face other directions. They look they all look same direction. This is a sample of movies I used these techniques. Movies of Saturn's ring. Very large number of particles are rendered in the scene. But of course, very near object must cannot be billboard. Using billboard for very near object is not reasonable. So compositing with near object using polygons and far object using a billboard is important. In this scene, there is about 6 billion particles in the view, and near objects are rendered polygons, and these vast particles are rendered by billboards. So using these techniques, you can render very large number of particles compared to polygon rendering. Okay. This movie of Saturn ring would be shown in not excursion, next session. Next session at 42U Dome. Okay, and the next topic is making very large particle data. Illustris is one of the most ambitious cosmological simulations, using about 10 billion particles. We used this simulation for a movie, The Man from the Nine Dimensions. We attempted to make fly-through movie with this simulation in this movie. But how? There are two types of data of this simulation. In full box, full particle data is stored in about 100 time steps. Very large data. And in sub-box, a part of the simulation box, more frequent time steps, but much smaller particles. In my techniques, we must have all data in my PC to render this data. So unfortunately, I cannot render these particles. It is impossible. So reducing data was very important. One important thing is some part of original information is not necessary for visualization. So we can omit several parts of original data for visualizing. And next, I used half float for saving the data. Using two techniques, I reduced data for visualization from original data. Using half float, X and Y and Z, and several other parameters, I used only 2 gigabytes for one step. So some extra data is needed, but much reduced. So I get files and reduced files and to clear hard disk, remove the original data and get files and make reduced data and repeat and make reduced data for visualization. And rendering full box is more difficult task. Showing full particle is unfortunately impossible. So I made several sets of data, much reduced data set. And I made fly-through movie so that sometimes camera is near its simulation, border of the simulation or outside simulation. So we make copied instances in the movie. So if data has 0.25 billion on, if data is this number, you may need to render 1 or 2 billion particles in this case. And next, I used reduced data. So we need is only a part of data. Then we need download a part of data. Unfortunately, not. In supercomputer simulations, these simulations are executed performed in parallel. So its data is divided to irregular multiple blocks. So I must download all data to make reduced data. This is very troublesome. Very large data must be downloaded. So this takes much part of my movie making process. So this is a really problem. And finally, I make about 25 reduced data files, not full intervals. With 5 time step intervals, about 25 reduced files, and make movies from this reduced data. If camera is fixed one, just overlapping data is enough to interpolate. But if camera is moving, some tricks must be used. I make two movies with same camera passes with offsetted data, and interpolate it, blending these two movies. We make interpolated movies with moving camera. And this is sample of camera works. I started movies near the at the sub-box simulation box. In this sub-box intervals of data is very short and smooth time lapse is achieved. So we can see the evolution of many galaxies near the camera. And then I zoomed out to full box scene. Of course, seamlessly. We not scene changing. I made seamlessly continued the camera path to full box, zoomed out to full box scale, and then zoomed out to looking with copied instances, very zoomed outside. In this final scene, we use several copied instances. So about 1 or 2 billion particles are rendered. And with these techniques, I barely achieved the time-lapsed fly-through simulation movie with very large number of particles. And this scene using Illustris is used in the movie The Man from 9 Dimensions. This movie is shown in Dawn Festa first day, and this is final slides. It's over. So, thank you.
So I'm now picking up my appropriate MC duties from Sho-san. So do we have any questions? We're a little behind schedule, but we have some time. Carter-san.
How long is the sequence? I'm very sorry I will not be able to attend the Dome Festa. How long is the sequence rendered?
Sequence I forget the exact length, but about 1 or 2 minutes. I guess 90 seconds for this Illustris scene. I guess.
Thank you. That's always a good length, I find, for dome production, for a scene. Thank you.
All right, thank you very much. Oh, Mark. Moved.
Some really clever techniques with billboarding, and so here's one thing. I need my hands to describe this. When you have two large billboards next to each other, oh, thank you, and they're camera facing, they'll intersect. Is that a problem? With intersecting camera facing billboards?
Yes, that can be a problem, but if particles billboard is often used about the particle size of the billboard, and particles are separated with that scale. Properly simulated data in properly simulated data, each particle are separated in about particle size. So there is no intersection of polygons in billboard. In general, sometimes that problem occurs, but in general, that is not matter. That does not matter.
Well, I'll just say that if you want to see a demonstration of what that problem looks like, I'll have a clip later today in the Dome Theater.
Very good. Well, thank you once again. Tane-san. So our next speaker is Hirotaka Nakayama from NAOJ to talk to us about data visualization with Unity.
Hi everyone, my name is Hirotaka Nakayama. I'm in charge of making visualization movies and 3D CG modeling at four-dimensional digital universe. Today, I'd like to talk to you about data visualization with Unity. And I would like to give some demonstrations. She's very worried, but don't worry. I will do my best. I will divide my presentation in these parts. First, what is Unity? And next, I will introduce an example of data visualization with Unity. In these parts, I will give some demonstrations and conclusion. First, what is Unity? Unity is a cross-platform game engine, and it is mainly used to develop video games. And this is the Unity interface, and these are examples of games produced with Unity. For example, Pokemon Go was made with Unity. Not only games, various educational contents are also being developed with Unity. This is Experience Curiosity on NASA's website. We can operate the rover Curiosity. And this is Team Lab Body. We can learn about human body. And this is Unity website. Unity has 4 license options, and Unity Personal is free. If you don't earn more than $100,000 per year. Okay, next. Example of data visualization with Unity. First of all, please watch my latest work, sample movie. あれ、こちらの画面が映らないですね。 in this movie, particle number of particle is about 15 million, made with only unity. H2 region. This simulation by Junichi Baba. I'd like to give a demonstration of making a visualization application with Unity. Today I will make a simple data viewer. The data is like this ASCII data. Each line shows one data, and these columns shows coordinates and radius and color values. And simple data viewer's flowchart. Data is visualized with this flow. First, data is read by C# script, and the data is stored into structure array. Next, prepare a compute buffer and set the structure to compute buffer. Compute buffer is the data array that can be placed on the GPU. Next shader. First shader is vertex shader. Vertex shader gets vertex values from compute buffer. Point data only. Next shader is geometry shader. Geometry shader makes billboards at each data point. Finally, fragment shader draws the screen. This is simple Unity scene. Play. There is only Unity-chan. And when I drag the screen, camera rotate. And this is C# script. Number of lines is about 100. It is very simple. When the application is executed, first, this start method is called. Prepare materials first. And next, this method is called. This method reads the data and store it in atom structure array. Atom structure is here. position, radius, and color values. First, in this method, first count data rows and prepare atom structure array for data points, and data is stored into this structure array here. Next, prepare the compute buffer and set the structure, atom structure to compute buffer. And set compute buffer to material. In flowchart, this C# script is here. Next shader. This is shader. The shader model specifies 5.0, and this structure buffer is just, has same structure as a compute buffer, and this structure is used to pass data from vertex shader to the next shader. Vertex shader is here. Vertex shader gets values of each data point from compute buffer, and these values pass to the next shader. Next shader is geometry shader. Geometry shader makes billboards at each coordinate, and pass billboard vertex coordinates and texture coordinates and color values to the next shader. Next shader is fragment shader. Fragment shader draws the screen from the texture and data color values. Okay, I will return to Unity work. In this screen, in this scene, I create empty game object. This is empty game object, and add C# script to this object. C# script is displayed on inspector panel. This is data path, and select shader and select texture. It is complete. Let's play. This is some molecular model and Unity-chan. ASCII data is read and displayed. By using shader, various expressions become possible. For example, fog effect and lighting and various blending modes and so on. Let's add fog effect to the scene. How to make is same as before. first create empty game object and C# script add C# script to game object, and this is fog color, and this value is fog saturation distance, and this is the path to the data, and select shader and select texture. Okay, let's play. This is some molecular model of virus, and fog effect is displayed. And this is C# script. The change is here and here. It's very, very simple. And this is shader. This variable is fog color, and this variable is distance from the camera with the fog becomes 100% opaque. These values are changed from C# script. And in vertex shader, fog opacity is calculated. And in fragment shader, fog color is overlaid. Okay, next. You can download the sample scene from this URL. Next, let's make a DOM master with Unity. Format of recording DOM images, for example, DOM master and equirectangular and cube map, and so on. And these formats are possible to mutual conversion. If you want to make a DOM master with Unity, to make cube map images. To make cube map, you have to place 6 cameras in the scene: front, left, right, back, bottom, top. But she said burdensome. So I created a C# script that automatically saves cube map images. This C# script. Download from here. This is particle scene. In this scene, this scene's camera is here. This main camera is this scene's camera. To this camera, attach the C# script, cube map screenshot. Okay. And if you save cube map images, you have to press Enter key. cube map images saved in these directories. Front. Next, how to convert cube map image to dome master. It is easy to convert cube map image to dome master by using Ectant free. This is free software and download URL is here. Ectant website is here. Convert and angle adjustment and color correction and viewer. It is free. I want to convert cube map to dome master. Input view and export view. And open cube map images. Cube map image is red. This is dome master. And convert, if you export, if you want to export, press this convert button and input resolution and select format and render. Dome master is exported, converted. Conclusion. Particle simulation results are able to visualize with Unity. It is also possible to visualize large-scale simulation results with a particle count of tens of millions. A dome master can be made by going through QMAP images with which were exported from Unity. Ectant is recommended for conversion from QMAP to dome master. This is URL. From now on, I would like to also visualize fluid simulation results. Thank you very much.
Very good. We have time for just maybe one question. Going once, going twice. Carter, making Shosan run all the way to the back.
すいません Do you find Unity limited, frustrating at times as a package?
Limited, sorry.
Do you find it sometimes not good enough limited in its ways.
Bad point in Unity.
As a package, it has limitations. Do you find those limitations difficult sometimes?
No, it is very simple, and I think it is a good tool for me. という感じでしょうか。
I guess art is all about working within constraint. So within the tool. Okay, thank you.
Thank you. You are welcome.
Okay, thank you very much. I think we have we need a connector for a Mac.
Oh, okay. Sure.
Oh, sorry.
I will answer to Carter about the limitation of Unity. Unity is a great tool for the real-time content, but for the serious use, for example, Unity uses C# or such kind of interpreter or intermediate language. So using the heavy computation in CPU, its speed would be limited, and garbage collection or such smart but heavy memory manage will also cause a problem. And usually the Unity or Unreal Engine is designed for the single computer and mostly the single display use. So if you want to use Unity or such kind of game engine in multi-channel dome environment, it will have more problem. Usually the open space view or such real-time big size visualization application use a cluster work, but using the game engine for such very precise synchronization in the cluster environment is still difficult because more loose connection is used for the real-time games.
I have an announcement very in short time. All presenters, please give presentation file, if you may. Please put Hatano-san. Please copy of the presentation file. We are waiting. Thank you.
Okay, very good. And for the last presentation of our afternoon session, we'll be ending with Ian McLennan. Of course, I screw up your name. Ian McLennan, who will be talking to us about innovative and new immersive exhibitions.
Thank you, Ryan. And I'm very happy to be here, and greetings to everybody, including the audience out there in internet land. Excuse me.
Mirroring. Which one?
We did have it on the screen a minute ago.
PC でいいはずですね。Could you finish your presentation and show the mirroring? Escape. Oh, it came. Okay.
All right. Don't know what was happening there. So I'm a Vancouver-based consultant working in museums, science centers, planetariums, world expositions, and IMAX theaters. And one of the projects I'm working on at the moment is I'm in charge of the master planning for Lowell Observatory in Flagstaff, Arizona, focused on the guest experience. And I've also been asked to do another project in nearby Grand Canyon. So Grand Canyon, of course, is one of the great wonders of the world, and there is an IMAX theater there. You'll be interested to know that visitors spend an average of 18 minutes looking at the Grand Canyon, but they spend about 35 minutes watching an IMAX film about the Grand Canyon. The Grand Canyon is located, of course, in Arizona in the United States, and there is a small town called Tucson, which is the home of this IMAX theater. I wonder if you could get these lights out, please. The center lights. The IMAX theater is not terribly distinguished by great architecture or design, quite the opposite, in fact. The original philosophy of the IMAX Corporation was to design black box theaters and concentrate on product on the screen itself. But there is a film called Hidden Secrets of the Grand Canyon that's the most watched IMAX film in history. But what to do in Tucson at night? Well, there's just about nothing to do. So one answer to that is to have an astronomy show, and the idea was to do it in the IMAX theater. In other words, to put an astronomy show on the giant IMAX screen, flat screen, instead of on a dome theater. So we've concocted a program that will allow us to look at the night sky, the daytime sky as well, to bring up the subject of dark sky initiatives, to talk about the natural history of the region, to talk about the historical aspects of the Lowell Observatory and the astronomy that's associated with that, including the local story of Mars and Pluto, contemporary investigations of those objects in space, and astronomical discoveries beyond the solar system. And of course, there are interesting cross-promotion opportunities with Lowell Observatory, with Kitt Peak, and with Meteor Crater, and there are a number of other scientific institutions. So the show will begin with a cosmic zoom kind of idea that takes us from the extremities of the known universe to Arizona. So there'll be this cosmic zoom that gets closer and closer to the Earth, and finally resulting in a meteoroid that hurtles towards Earth, plunging into the Arizona prairie, which is a desert. This was a prairie that was populated by camels and horses at the time of the meteor strike about 50,000 years ago. And it was, of course, a cataclysmic event resulting in the famous meteor crater that is in Winslow near Flagstaff. And it's visited by a huge number of people every year. So there's a cluster of activities around Flagstaff that all have an astronomical connection. Part of the cultural history of the region includes Percival Lowell, the wealthy Boston businessman who staff in 1894, looking for an ideal spot to observe the opposition of Mars in 1896. And he owned part of the railroad at the time, so he got free passage all over the place. And one of the places he landed at was Flagstaff, where he finally decided to build this giant observatory. And of course, it's a well-known story that Percival Lowell endowed this amazing place with the Clark telescope and with other devices that allowed him to observe Mars as close as it could be observed at that time. And he made astonishing discoveries at the time, but he was fixated on the idea that there was life on Mars. So this production on the screen, on the IMAX screen, will include a zoom beyond the Clark telescope, closer and closer till we get to Mars, relating it largely to his discoveries or his observations of the time, attempting to analyze the markings on Mars that he assumed were created by Martians. He was quite fascinated by that concept. And of course, the whole idea behind setting up this telescope at the time was to prove that these lines on Mars were artificially created. Well, of course, we've come a long way since then, and we now have rovers and spacecraft that are resident on Mars, haven't discovered life that Percival Lowell was looking for. Eventually, I have no doubt that we'll find evidence that there was once life on Mars. And the giant IMAX screen will be quite spectacular as it can contain panoramic views that have been obtained by these spacecraft roaming around Mars. Relating it back again to Lowell Observatory, one of the local attractions, we will be able to tell another story about the discoveries of Lowell finally resulting or culminating in the discovery of Pluto in 1930 by Clyde Tombaugh, who was there's a very compelling American story there. He's a farm boy who wasn't educated in astronomy, but was such a magnificent observer that he became known as an astronomer, and of course even more famous that once he discovered or detected the object once known as the planet Pluto. That gives us an opportunity to investigate the data that have been collected with New Horizons and incorporating some of the things we saw yesterday, and that will take us to Pluto and beyond. And there's some wonderful opportunities, I think, to really use data visualization to its full force on a big IMAX screen. We'll also be looking at just simply what's available to observe for the night sky above Flagstaff and the region, and so we'll be looking at the stars of summer largely, although the people who own that theater are considering seasonal shows for all four seasons. There's an opportunity to talk about dark sky as well. This is a view of Las Vegas, Phoenix, and Tucson, and there's a great deal of attention being paid in those, especially in Arizona, to dark skies. And of course, it becomes increasingly important as our lights increase the pollution of the area and the light pollution. We'll also be making reference to the observatory and looking at the sky, the objects in the sky, which will allow us to, through data visualization, project the eventual collision between the Andromeda Galaxy and the Milky Way. We'll end the famous sunrise scenes on the Grand Canyon, which give us all kinds of opportunities to celebrate the natural. We also want to celebrate and acknowledge the skies that were observed by the Navajo, by the Nahopi, and other native cultures of the going back thousands of years, and recognize that there were simply different ways of knowing the universe, and dating all of that back to the fact that the skies belong to everybody. The admission is free. It'll end with credits, and I wanted to mention one other thing, that there is lots of opportunity to, as I mentioned, to use planetarium software in this program on an IMAX screen for the first time. And a year ago, we conducted an experiment at the IMAX Test Theater, so pushing planetarium software through an IMAX digital projector, and a test conducted SkyScan and with the Ontario Science Centre. We actually determined that pushing that software, the digital sky software, through the IMAX system worked, with one notable exception, that although we could look at the orbital mechanics and see a beautiful rendition of the night sky, and looking at visualizations created by Pierre Boulanger at the University of Alberta, we couldn't really look at things that had extensive lateral movement because of the 30 frames or 24 frames a second on the digital IMAX system. And of course, planetarium software requires a great deal more than that. So there's a lot more to be investigated, but at least we proved the concept that planetarium software can be pushed through an IMAX system. Thanks very much. Thank you.
Thank you. Do we have any questions?
Thanks again.
I think Carter has a question.
Sorry, I'm always asking questions. The SkyScan system is capable of 60 FPS, so the IMAX system was not, apparently. It's a digital system, right?
That's correct.
So it was, that's interesting. In New York, we have a 4K system. We decided in our large format theater, it's not IMAX, so we chose another system. But with 4K, we had done our Pluto broadcast to planetariums around the world, but we actually used our large format theater for the Pluto visualization because we had 200 extra seats for that theater. And you should come to New York to see Mars at 6-meter resolution flyovers in stereo on that. And that should be part of your show.
I'll consider
Especially
that.
the canyon proximity or analogy. So anyway.
I'll consider that an invitation.
Is it a stereoscopic dome in Arizona?
No. Yeah, okay. The Grand Canyon IMAX is a film system. It's the 10th projector that was produced by IMAX Corporation, so it's steam-driven. But the projection system that we used in Toronto for the experiment, of course, was the most up-to-date laser system, laser digital. Yeah.
I think we have a question from Doug. I'll save you the walking.
Yeah, I was just at Lowell last summer and just loved all the programming there. And I know they have a lot of engagements with the staff, giving talks and so forth. And sometimes they do it in historical buildings and around the telescopes and stuff like that. Are they going to be presenting in the large format theater their science or scientific results where you have astronomers facilitating that?
That's an interesting question. They've offered to cooperate, and they've offered to do the scientific analysis of the show, just in terms of accuracy. So we'll be using them for that part of the show. Ultimately, we'll be looking at different cross-promotion and opportunities between the three attractions that have an astronomy base. But it's still fairly early stages of planning for the Lowell expansion project, but it will include a major new visitor center, an outdoor planetarium, open sky planetarium, and expanded observing facilities for the public as well. I don't know if that answers your question, Doug. Yes. Thanks again.
All right, thank you.
Thank you. So, I have very, very important announcement. We have to move 42 Youth Theater from now, and nothing remains this room. Nothing remains this room. Please move to 42U Theater. I hope we would like to start about 2:30. Hope the next session at the 42U Theater, but maybe delay. But please move to 42U Theater, please. Thank you. And also someone there who present your file to Hatano-san. Please, your presentation file